Okay, now a little bit of this I think you'll find is a slight review of what we did last time, just because I wanted you far enough along so you could do the lab last time. So we'll be reviewing a little bit of that and new stuff as well, and then we'll try to wrap up the chapter. Then we'll get started in chapter 6. We skipped chapter 5. We'll go to chapter 6. And I just have a suspicion that we probably won't get far enough in chapter 6 with enough time to do a lab in chapter 6. So today's probably going to be sort of a marathon, a little bit longer, mostly lecture as far as I know it will be. And then we'll look forward to Tuesday of next week. We will have gotten far enough for the lab by then. So we'll have the first lab, we'll continue with chapter 6 for about 2 hours, do the first lab on chapter 6, which I don't think will take you 2 hours, but I'll allow you 2 hours, and then we'll have the test on chapter 4. So, make sense? Got it? All right. Any questions on anything we've done so far? Okay, continuing in chapter 4, which is heat and temperature. We've already covered sort of the temperature part. We're still on pretty much what we consider the heat part. But we're going to move into a little bit a few other areas as we go here. It's not all temperature and heat. There's some other areas as well. Now, I think I mentioned this before too. It seems like, I'm going to go back one slide. Okay. This was the first slide in energy, heat, and molecular theory. 2 responses of matter to heat. And probably the first one you would think of is the temperature goes up. If you heat something, typically its temperature is going to go up. Not always, though. That's only with it if you're within a given phase. If the material's a solid, you heat it, it becomes a warmer solid, generally. Okay? If it's already a liquid, you heat it, it becomes a warmer liquid. You have a change of temperature, but it stays a liquid. Or if it's a gas, you heat up the gas, it's just a warmer gas. In all those circumstances, the heat goes mostly into the internal kinetic energy, which, what's a measure of average internal kinetic energy? Temperature. Temperature. That's what temperature measures, is average kinetic energy of the internal molecules. Now, the measure or the parameter we use to determine that is specific heat. Okay? Now, we did this in class in several problems, and you did it in the lab last time. Anytime you're heating a material within a given phase, you add heat to it, the temperature goes up because the average internal kinetic energy goes up. And specific heat for that material is what you use to determine how much heat, how much temperature change, whatever. Okay? Make sense? All right. Here's generally what they're speaking of then. If you have a solid, now they're showing ice, and I sort of regret they do this right here. It's okay, but it's showing the next slide as well. If you have very, very, very cold ice, when you first take ice out of the freezer, have you ever noticed that if you handle it, especially with slightly dampened hands, does the ice melt in your hand? No, it freezes the water on your hand, and then you're stuck with it, okay? Now, I don't know if y'all saw the Christmas movie. I think it's just called A Christmas Story. You know the one I'm talking about? He's after a red something, another bike or rifle or something. You know, it's what the kid wants for Christmas, right? I can't remember the whole story. But there is a part of that story that sort of is illustrating what I'm meaning there. And it just happens to be that my wife's brother had a very similar experience, okay? It wasn't a flagpole outside in the freezing temperatures because they were living in Huntsville, Alabama, and they didn't have that cold to freezing temperatures up there. But it did happen in the grocery store, okay? Karen's mom had the two younger kids, Keith and Terry being the younger one, in the store with her while she was doing her shopping, rushing around. And Keith, of course, had wandered off somewhere. He was probably a preteen boy, and Terry was, grammar school type age. And Mrs. Brazil was about finished her shopping, and she said, "Terry, where's Keith?" She said, "Well, I don't know. I saw him back." "Okay, go get Keith. I'm getting ready to check out. Go get Keith." So she went back, and there Keith was leaning over the ice cream freezer, or what's one of those freezer compartments there, and just leaning over there. And Terry went and said, "Keith, come on, Mom's about ready to go." He said, "Hey, go ahead, Mom." "Okay, what? Go ahead, Mom." What he had done, all that nice looking, it was a hot summer day, and that nice looking frost was there on the freezer, so he thought he would bend over and lick him some nice cool frost. Of course, that nice cool frost was well below freezing, and the nice liquid water in his saliva, when he put his tongue down, froze right to that nice cool looking frost. And Terry ran to get her mom, tried to tell her what had happened. Her mother was horrified, okay? Went back there and just was so embarrassed that her son would do something so ridiculous as licking the thing and getting his tongue stuck. And rather than make a scene in the store and have to admit to having such a child as this, she just took him by the collar and ripped. Blood started pouring everywhere. She hustled him out of the store, left some of his skin there on the ice, and it was not a pretty sight from what I'm told. Now, the reason I like telling that story is Keith Brazil is Mr. Cool. I mean, he was a high school basketball player, a college basketball player, one of these obnoxious people who looks great, he could do just about anything, math major in college, and very successful businessman in his hometown, and chairman of the school board in his hometown, which is no longer Huntsville, Alabama, where someone might know of that story. It's down in Louisiana. So I'm not even sure his kids know that story, but we enjoy telling it every chance we get to watch his embarrassment. Okay. So if you have ice at a very cold temperature, it doesn't melt. You add heat to it, it just becomes warmer ice. The temperature goes up. And the specific heat for ice, if you remember, is 0.5. Okay? Not 1 like water, but 0.5. Okay? Now, we didn't do that in the lab. We had ice already at 0 degrees or close to it. Well, then the next thing, so right then, all you're doing by adding temperature is making the molecules vibrate faster. They're in a solid, they stay in the solid, they just vibrate faster until finally it reaches a place where they start breaking away and the ice becomes a liquid. Okay? Now, as long as that ice is liquid, or is in the presence of a liquid, what it's done then, if you think of, and we'll see a graph of it later, you add heat, the temperature goes up because it's in a given phase. It goes up until it reaches the melting point. And at the melting point, you add more heat. The temperature does not change like it did back here within a given phase. Now, you add heat to those molecules, and they start breaking away from the crystal lattice that they were in as ice. Okay? And some of them become liquid. And that keeps happening at the same temperature. And you remember, one of the questions in 2 labs ago was, did the temperature change as the ice water was warming, as heat was being absorbed by the ice water? And if you had looked at your thermometers, I kept reminding you, I said, go back and see if it's changing any now that it's equilibrated. And it wouldn't. So the ice was still melting as long as the ice and water together, it's going to be right at 0 degrees. Now, your thermometers may have been off a little bit, as you noted in your lab, but it was still constant. Okay? But when all of that ice finally melts, you're adding heat to the ice and it's melting, not changing temperature, but when it all finally melts, you add more heat, now the water starts increasing in temperature. But all that time, the ice warming, the ice melting, as you add more heat, the temperature doesn't change. Water warming, the temperature is increasing. Again, you use specific heat there. Specific heat for water is 1 calorie per gram degree Celsius. It just keeps. Ice was 0.5, water is 1. It keeps heating, keeps heating. Now, the water molecules, we're free to move around. All they do is vibrate faster. Okay? And that's why the temperature is increasing, because you're increasing the average kinetic energy of those molecules. Until finally, you reach the boiling point. And at the boiling point now, some of those molecules break free from the other. Because remember, water has a strong cohesive attraction. We call it surface tension. Those water molecules hang on to each other like crazy, but when you add enough heat, they break free, and each molecule now is free to go, and we call that steam. As you can add all the heat you want to, but until all that water evaporates, your water is at 100 degrees Celsius, 212 Fahrenheit. Adding heat does not change the temperature there. Adding heat to cold ice changes the temperature. Adding heat when ice is at the melting point does not change the temperature. Adding heat to water when it's above the melting point changes the temperature. Adding heat to hot water when it's beginning to boil does not change the temperature at all. All you do is create more steam. But once all the water has evaporated, adding heat to the steam now makes it superheated steam. That's typically what they use in generators, power plants, things like that, except for hydroelectric, of course. It says very, very high superheated steam, high temperature superheated steam. So anytime you're within a phase, you add heat, you give the molecules more internal kinetic energy, they speed up, and the temperature goes up. You use specific heat there. When you're in between the phases, like this, same slide, okay? The second way is when you have a phase change. When you add heat at a phase change, the temperature does not change. You're at a constant temperature, and now you're related to the changes in the internal potential energy, not kinetic energy, okay? And the type of heat we use then is not specific heat, but latent heat. And we did use this in the last lab for the melting of the ice, okay? And that's the latent heat. Which latent heat was that? Melting of the ice. Latent heat of? Oh, how rapidly we forget. It was a good 2 days ago, right? Latent heat of fusion. The other latent heat is latent heat of vaporization. Okay? Now this is the graph that was doing what I was waving my arms about before. Okay? When you're warming very cold ice, adding heat to it does increase the temperature. Use specific heat of the ice. And here's Shanika. We broke double digits. Good. Okay. When you do reach the melting point of ice, adding heat does not change the temperature, but changes the phase from solid to liquid. That's why we call it melting. If you're going the other way and removing heat, you call it freezing. Same temperature, same everything. It's just whether you're adding or deleting heat. Pulling off heat. Now, while we're here, and we did it in lab, but let me do it again here, give you the latent heats. We already had the specific heats before. Let's do the latent heats. Okay? Latent heat of fusion, now we'll use water since they're doing here. Different for every substance, okay? Latent heat of fusion is 80, I believe it's 0.0 calories per gram of water or ice or whatever you're dealing with. The latent heat, I can't write, of vaporization or condensation, okay, is 540.0 calories per gram. So you see it takes even a lot more heat to break that strong cohesive bond that water molecules have for each other than it does to break the bond, the crystalline bond the ice has holding it together. Quite a bit more. Okay? Now, with that in mind, then your Q, remember how we had the formula for specific heat? The Q here is now ML, whichever L it is. Notice you have no delta T here, right? Why? At changes of phase, you don't have a change of temperature. There is no delta. It's just the mass of the material, there's the grams, times the latent heat, calories per gram, that gives you calories heat. So same illustration we had before. This represents warming the ice, specific heat being 0.5, melting the ice, latent heat being 80 calories per gram, warming the water, specific heat of water, 1.00 calories per gram degrees Celsius. See, both of these have degrees Celsius because you're changing that. You get to the boiling point or the condensation point, whichever it happens to be. You have no change of temperature, so you go back here, and then it's the mass times the latent heat of vaporization, which is quite a lot of heat. Okay, now on that, kind of on the same subject, ever go home, really hungry, you want to fix up something quick, turn on the pot, get the water boiling. I want it quick, so I'm going to turn up the heat. Is your food going to cook any faster? No. Because you can't get any hotter than the boiling point of water as long as all it does is boil the water faster, but doesn't increase the temperature at all. All you do is boil your water away faster. And if you're not careful, then whatever you're trying to boil, the corn, the peas, or whatever it is in that pot, now you're going to scorch them because all your water evaporated. And then you can't eat them anyway, or they really taste pretty bad. Okay? So usually, Mama probably told you, is once it comes to a boil, put a lid on it and turn down the heat. All you have to do is maintain the boil. You don't have to get it boiling. It won't boil any faster. It may evaporate faster, but it won't heat any faster. Just put on a lid and turn down the heat. Let it cook. Don't take the same length of time. Now, as we said before, though, when you're in high elevations, you're probably going to have to cook longer because the boiling point is a lower temperature the higher the elevation. Okay, you lower the atmospheric pressure, you lower the boiling point. Okay. Oh, I never did quite get there. Okay, so here you use latent heat of vaporization, 540 calories per gram times the mass of the water that's boiling. Then, once it becomes water vapor, you're back to specific heat again because you're changing temperature, and the specific heat of steam, does anyone remember it? Surprisingly, almost the same as ice. It's 0.48 calories per gram degree Celsius, whereas steam or ice is 0.5. Water, though, is 1. Any questions on that? We did the parts in the lab, basically, we stayed in here. Melting of ice and warming of water, or cooling of water. Okay? Now, here's a table, I think it's fairly wimpy table, that shows the names pretty much. I don't even think they show this table anymore in the text, because it is fairly nothing new here. But these are your phase changes. When you're going from a solid to a liquid, of course that deals with a latent heat because you're changing phase. That's the latent heat of fusion. Okay? When you're going from a liquid to a gas, again a phase change. That's called the latent heat of vaporization. You can, in some circumstances, Mark Will here when he sneaks in without telling you, okay? And there's Will. Okay, anyone else come in? I don't see anyone, okay? Some materials, and actually water will do it too, but it won't be at normal temperatures and pressures, okay? Carbon dioxide does this. It goes from a solid to a gas in one step. You'll never see a puddle of carbon dioxide. If you got, anyone know what they call solid carbon dioxide? Dry ice, right? And if you've ever dealt with it, have you ever seen a puddle of liquid carbon dioxide? No. It goes directly from a solid to a vapor. That's called sublimation. And it happens at certain temperatures and pressures. And for carbon dioxide, that's way below what we have as normal temperatures and pressure, and at a lot more pressure. Okay? Now, when you have, what's the temperature doing that? Well, the temperature stays, when you're going from solid to liquid, it stays constant, and it stays constant at the melting point. That's what we call it. When you're going from liquid to a gas, the temperature stays constant at the boiling point. For water, this is 0 degrees Celsius, 32 Fahrenheit. This is 100 degrees Celsius, 212 degrees Fahrenheit. And when you go from solid to a gas, it's just called sublimation, okay? There's no new term for it's just a sublimation point. Now, what if the temperature was heading this way? In other words, you're starting with the gas, you're removing heat, the temperature is dropping. I wish they wouldn't say temperature. It would be the heat is decreasing. That's one reason this is a pretty poor table. If you're going from a gas to a solid, which would be what you did with carbon dioxide when you're cooling it, go straight to that. It's also called sublimation. They don't have any new terms here, okay? But when you're going from a gas to a liquid, we call that the condensation point. Same temperature as the boiling point. It's just whether you're adding heat, boiling point, removing heat, condensation point, okay? And when you're going from a liquid to a solid, you call that the freezing point, of course. But it's the same temperature as your melting point. It's just whether you're adding heat or removing heat. So there is some value to the table, but it's a bit bizarre. They should be saying heat increasing or heat decreasing. Because at these points, there is no change of temperature. Well, I know what they mean. Up until then or past then, that's where your temperature is setting. All right, so now let's look at evaporation and condensation. We mentioned those points. We haven't done anything with it. They're a little bit harder to work with. And okay, here we go. Before we do, there is, okay. Back on what we did before when we talked about heat transfers, sorry, conduction, convection, and radiation. There's a little concept supplied at the top of page 101, because we're right at the end of the class, I didn't notice it. That's there, and there's 3 experiments you can do on heat flow, and each one of those gives you something you can play with there. Okay, you don't have to, but if you want to look at it further. Okay, phase change, we've done that. Heat of fusion, the formulas I had here, I only gave you one, but it's the Q is equal to m sub L F, or Q is equal to m sub L V. There are equations 4.5 and 4.6 in your text. And there is, and this is going to be something coming up a little bit later, but we sort of talked about it before too, the passive solar design. How you can use solar radiation either to, well, basically to save you some money, okay? And we got Travis here. Let's find them. There you are. Okay. And we have JJ here. Has anyone else come in since Chicago? Okay. And I told the others before y'all got here, all who've come in recently, it's looking right now as if today is probably we won't get enough done to do a new lab. Okay? Here's Coco. Okay. Anyone else? Okay. We got to finish chapter 4. We've done all the labs for chapter 4. And that's what we're in the process of doing now. And of course, we're skipping chapter 5 if you have the big books. We don't do a chapter 5 if you have the thin book. It doesn't even have a chapter 5 and it goes straight to 6. And we'll get into 6, and that's the electricity and magnetism lab. Well, we got to cover a certain amount of stuff in there before we're ready for the first lab there. Just my gut feeling, we probably aren't going to have time to get everything covered, the rest of chapter 4 and the beginning of chapter 6 covered, and to allow ourselves 2 hours for the lab. So the day probably is just going to be pretty long lecture day. Okay? Now, we'll see. All right. But then on Tuesday, let me go on and say this too, I said it to the others. That means on Tuesday, we'll only have 2 hours of lecture. On chapter 6, we should be in by then. Surely we'll go far enough to have a lab then. Then we'll have 2 hours of lab, but the last 30 minutes will be the test on chapter 4. So be prepared for that next Tuesday. And any of you, I think all of you took chapter 3. And let me say this about that too. I have a huge stack of grading to do. The last few days, they've been calling meetings and having things like the Honors and Awards Day and all that kind of stuff, which really bummed into my office hour time. I don't have many office hours now, and when I've gone home in the evening, I'm just so exhausted, mostly because of the treatments I'm taking. I'm just worn out at the end of the day. I started grading last night and literally was falling asleep trying to grade the paper, so I just laid down and went to sleep. Okay, sorry. But the passive solar design is here on page 103, I was saying before some of you came in. We talked about some of the material there. I'll let you read it, and any questions you have. Pretty good little blurb. I mean, it's a big blurb, one of the full-page blurb. Okay. Going on down, there's a science sketch there, which we sort of talked about, so you don't need to do too much on it. But there is a table here. I wish they had put in the book, but they haven't. Maybe rather than that table. And that's the one, 4.4 in your book now. It's going to be sort of hard to see here because this isn't very light color. But it's on the specific heats and latent heats for water. And I've already mentioned them in a couple slides ago, just so you'll know where to find them. Water has specific heat of 1. Ice has specific heat of 0.5, 1/2. Steam has a specific heat of 0.48. Okay, almost the same as ice. Latent heat of fusion for water, 80.0 calories per gram. You used that in the lab last time. And we didn't do latent heat of vaporization, though it was going on in the first lab we did in this chapter, and that's 540.0 calories per gram. Okay? And then they throw in again, because it's a pretty important concept, the mechanical equivalent of heat. 1 kilocalorie is, I don't know why they list them this way. Seems like to me they say 1 calorie equals 4.184 joules. They're about the same magnitude. 1 kilocalorie would be 4.184 kilojoules. But they list it as a kilocalorie as 4,184 joules. Why don't they just keep the units consistent? You know, kilocalories, kilojoules, calories, joules. The numbers are very, very close. Okay. Now, before we move to the next topic, which is evaporation and condensation, let's get the example 4.7 done. It's a lot similar to what we did in lab, only a bit more involved. How much energy? Okay, that's the question. What are we looking for? If the question is how much energy, what's this energy we deal with in this chapter? Heat and temperature. Calories, exactly. And what symbol do we use for that? That's the unit. What symbol?
C.
Say again?
Little c.
That's specific heat. Say again? I think someone said it.
CAL.
That's the unit for calories, yeah. But what's the symbol in our equation that stands for heat or energy? No. Capital
Q.
Q, capital Q, of course. Okay? So that's what we're looking for here, Q. Okay? That's what we're looking for. How much energy does a refrigerator remove from 100 grams of water at 20 degrees Celsius? Okay? So when they say 100 grams of water, what's that a measure of? That's what? Mass. Very good. At 20 degrees Celsius. Someone tell me about what 20 degrees Celsius is.
Room temperature.
Room temperature, exactly. I bet you we're not more than a few degrees off 20 degrees Celsius right now. I bet you that says 72, doesn't it? The thing above your head. Okay. 20 degrees Celsius is 68. So we're 4 degrees above that, but that's 4 Celsius, no, I'm sorry. We're 4 Fahrenheit degrees, so that's probably not going to be, it'd be a little more than 2 degrees. So we're about 22 and a half or something like that degrees Celsius. So right at room temperature, okay? 100 grams of water at 20 degrees to make ice at, what we're going to is to make ice at, this is water, ice at negative 10 degrees Celsius, which is probably pretty close to what your refrigerator does. I think it's around negative 20, I'm sorry, about 10 degrees Fahrenheit, which would be almost equivalent to negative 10 Celsius, somewhere close to it. Okay, we want to know how much heat is removed. Now, what's the first thing you've got to do to that water as you start removing heat? The first thing that's going to happen to the water. Start removing heat.
Freeze.
Second?
Freeze.
Not yet. Tell us, what is the water at? – 20 degrees Celsius. Water will not freeze at 20 degrees Celsius. Ever. Unless you're under an awful lot of pressure. No. I don't know if you have it. Not normal circumstances. So what's the first thing you got to do to the water? Cool it to get down to 0 degrees, the melting point, or freezing point. So what Q, what equation, what representation of Q do we use to cool water? I'm going to call it Q cooling. What formula equation do we use? We used it in lab, but going the other. Yeah, no, we used it in lab going this way, too. Changing the temperature.
MC delta T.
That's MC delta T, because you're changing temperature. And this is water. What was the mass of the water? 100 grams. What was C for water? Someone answered it already today. 2 people have, huh?
20 degrees Celsius.
I can't hear you.
20 degrees Celsius.
Okay. That's not C. That's a temperature. That will be in the delta T. What is your C?
1.
1. Okay, pretty hard, huh? 1.00, in fact. What units? These are the more important things. What units? Oh, you did it in lab. Calories per gram degrees Celsius. Perfect. Okay. And then what's your delta T? Second? 20, exactly. You only cool the water down to the freezing point, which is 0. So the delta T for the first stage of this is going to be 20.0 degrees Celsius. So that's your Q of cooling. All right. Now, this is pretty easy math here. 100 times 20 would be 2,000, right? Times 1 is still 2,000. The 1 is there to help you with the units because the grams cancel out, degrees Celsius cancels out, so you have 2,000 what? Calories. Little c calories. Okay, very good. Okay, so that's the first thing that your refrigerator has to do, remove 2,000 calories of heat from that water at room temperature. What's the next thing it's going to do? You got really cold water now, huh?
Cool it down some more.
I don't think it will, not at first. Tell us, what does it have to do next? Freeze it, which is not changing the temperature at all. So it's not cooling anything down, but you're still removing heat, but you're removing heat for a phase change. And what's the formula for that? You did it in lab, but you did it the other way. You're melting ice, but it's the same formula. Q melting. Anyone remember? I've written it on the board. In fact, it's on the board right now.
ML.
ML. Which L? There's 2 L's.
LF.
Second?
LF.
LF, the latent heat of fusion. And the mass, what's the mass of this cold water? What's the mass of this cold water? 100 grams. Okay, that hasn't changed. 100.0 grams. And what's your latent heat of fusion for water? It's on the screen too. You see it? Second? I can't hear you. No, that's the temperature. Latent heat of fusion.
80.
80, right there. Latent heat of fusion for water is 80 calories per gram. So you multiply this by 80.0 calories per gram. Okay? Notice here your grams go out and no delta T here because at phase change there's no temperature change. So what do you have? 80 times 100 is 8,000 calories. That's where a lot of your energy goes to make that ice. That's 8,000 calories. Okay? Now what has your refrigerator got to do? You've changed the water. First you changed it from room temperature to freezing point. Then at the freezing point you made ice. And now what do you have to do? Second? Lower the temperature again. So what formula will we use for lowering a temperature? This is cooling the ice.
MC delta T.
Absolutely. MC delta T. Okay? What mass of ice do you have now? 100 grams. That stays the same because you didn't lose any of it. Okay? What C do we use? Help me. Say again? Nope, because it's no longer liquid water. 0.5, excellent. What units? It actually is 0.500. What units? Calories per gram degrees Celsius. All right. And what's our delta T now? Okay, yeah, you're going to from 0 to minus 10, so it's a change of 10 degrees Celsius. Okay. Now, that's not very hard math either. It may be hard to read, but you got 100 times 10 is 1,000. We take half of it, and you got 500. So that last part is just removing 500 calories. Oh, and the units are grams go out, degrees Celsius goes out, and you're left with 500 calories. Okay? Now, what the question was, how much energy does the refrigerator remove from 100 grams of water at 20 degrees Celsius to make ice at negative 10 Celsius? You add those two together, and what does that give you? This one plus that one plus that one.
10,500.
Okay, 10,500 calories. Little c calories. That looks like a capital C. That's how much energy it took. Now, if you want that in joules, then you use the joule equivalent of heat. Okay? I would tend to go with, make that kilocalories and then use it for kilojoules, which makes the numbers smaller because you got a bigger unit. They didn't ask for that, I don't think. No, they just said 10.5 times 10 to the third. Well, it's just as easy to write 10,500. All right, any questions there? All right. If not, we now go to the next subtopic, which is evaporation and condensation. We've done a lot more with freezing cooling because that's easier to do. But what happens with evaporation and condensation? Now, if I had a pan of water here at room temperature, would any of it be evaporating? Unfortunately, yeah, it would. If you think about this, when we mentioned this and some of the graphs we've shown before, those molecules in that pan of water, some of them are moving slowly, some of them are moving fast. The temperature is the average kinetic energy, measures the average kinetic energy of those molecules. That doesn't mean they're all at the same average kinetic energy, because when they bump into each other, some of them may slow down and some of them may speed up. Okay? Some of them may get exposed to light and energize some. So you always have some outliers, you might say, that's different from outright liars, but anyway, that are actually at a higher kinetic energy. And when they get enough kinetic energy to break free, they do. So a pan of water here, in this environment, would very, very, very slowly evaporate away. Okay? And when I say this environment, we have conditioned air coming in. I don't know what condition the air is in now, but if it's in the cool weather, and that's warmer air, when you warm up air, it has greater capacity to absorb liquid. In fact, in the summer, in the winter, sometimes people get really dry sinuses and stuff because there's not much moisture in the air. And there's some areas of the U.S., like the desert areas, which is always such low humidity, especially in heating conditions, it really gets low. People, lips crack, nasal, things crack. It's just not a pretty sight at all, okay? And people actually humidify the air. Here in the Southeast, that's unheard of. If we do anything, we dehumidify the air, okay? Which, when we're cooling, that's exactly what happens. Just about all the air conditioner units have a pre-cooling mode that actually takes the moisture out of the air. And if you check any air conditioning unit, pretty much, you'll find a condensation tube, somewhere that's draining that water away. We built a little 2-bedroom bungalow over on the farm in Georgia, so when we go over there, we have a place to stay. and we might use it as a retirement home as well, but we're not far enough along for that yet. But we're still paying off the mortgage so that we might be able to use it if we needed to. The condensation tube was there right near the AC unit, and my wife thought, yeah, that's a lot of water going in there. What can I do? I like mint. Let me just plant me a little mint plant here, see if it survives. Because we're not there to water in the summertime because I'm here teaching, So, but she thought that's going to get water because the AC unit's going to come on, periodically. They always get water. We have mint everywhere now. It loves that soil over there, and it is really good, strong mint. And we brought a bunch home, and she made fruited mint tea, which is really, really good. So condensation, that's what we do in the Southeast. We remove the heat from it. So even in air conditioning, some people will have problems with sinuses drying out and stuff like this. Those kinds of people, you go out west where it's really dry, they suffer. But out there, they actually have humidifiers in their heating air conditioning system to add moisture to the air because it really will make people miserable. So there's always evaporation happening because some molecules are going to be at higher energies than others, and they may have high enough energy to escape. Now, there's another thing, I don't want to get into this because this book doesn't get into it. There's something they call vapor pressure, okay? And you kind of know the reverse of this from your automobiles. What kind of cap do you have on your radiators? Just the regular old screw cap? Dust screw, but
It's got a pressure relief on it.
it's a pressure cap because if you keep pressure on it, the boiling point goes up, right? Just like we talked about in the lab. So you do want a little pressure on there so it can absorb more heat, okay? And you blow that away. But there's a relief on it, so if it gets too high, then it leaves, okay? Well, where was I going with that? What I was going to say, on the other hand, if you reduce the pressure, then more molecules leave. So adding pressure, okay, here's another thing. Can you boil water at room temperature? What you think? Yay or nay? And I'm talking about water. Can you boil water at room temperature? How? Lower the pressure. And if you have a what do they call this pump? It reduces pressure. There's a name for it. I can't think what it's called. But if you start dropping the pressure, and you have to have a really good, strong container that it's in, start dropping it, and you'll start seeing bubbles come up, and after a while it's roaring boil at room temperature. Okay. So pretty low pressure, but it can happen. So, now that is overall atmospheric pressure. But if you have a lot of humidity in the air, then you have what we call vapor pressure. So if this room were at 100% humidity, just sticky, hot, high humidity, you're not going to evaporate any water because just as much water will come out of the air into the water if you're at 100% humidity. Most of the time you're not there, thank goodness, okay? So if you're at any lower, then more of those molecules are going to leave because you have a smaller, what they call vapor pressure up there, okay? Now, we're not talking about that now, but that's why a pan of water would evaporate over time. But here's what they talk about. Individual molecules can change phase at any time if they have enough energy. Remember, the temperature is only measuring their average kinetic energy. You'll have some molecules at high kinetic energy, some at low. If they have high enough, they can pop out, evaporate. Evaporation is energy is required to overcome the phase cohesion, the water sticking together with that hydrogen bonding. Higher energy molecules near the surface can then escape. Okay? In condensation, and actually, when I worked at Southern Research Institute, we were doing radon research, and some of the experts came down to help us at some, and we were at some professional meeting down in Orlando, Florida, which is warm and humid, very humid. And the place where we were staying happened to have an indoor pool right next to the room where we are, so the air was very, very humid. I mean, the AC systems couldn't get all that moisture out of the air fast enough. And this guy from upstate New York was one of the experts in the field, and he could not believe it. You pour a glass of ice water, because everybody was drinking water, because it was pretty warm down there. Pour a glass of ice water, and immediately condensation goes on that cup, because the vapor pressure in the air, water vapor pressure, was quite high. You get a little cool thing here, and it starts coming out of it. So you can be condensing like crazy. Gas molecules near the surface lose kinetic energy to the liquid molecules and then get back into it, or form on the edge of the glass. And he couldn't believe it can happen that fast. I said, Terry, look, next door, that's his swimming pool. We're at close to 100. He said, oh yeah, I guess you're right. It can happen that quick. Okay. So evaporation or condensation can happen at any temperature. Now here's what they're talking about here. Now these are just relative numbers here. They don't really mean anything. They're not representing any particular unit. But these are all water molecules, or whatever the liquid is, molecules. But these are the various energies they have. And it'll never be just like this. This is illustrative purposes only. Some of these are lower energy than the average. Some of them are pretty close to the average, and some of them are quite high. Now, the one thing that's a little bizarre about this picture, in general, the lower energy molecule, because they have less kinetic energy, they're not moving as fast and bouncing as hard, they would tend to settle down to the bottom, and then the 10s, that would be the 5s, the 10s would be somewhere above that, 15s here, but the 25s they have right. They're near the top because they're bouncing into each other, so they're less dense. So the warmer water tends to move toward the surface, probably will pick up a little energy on the surface too, and they may escape. Okay? Well, what happens then? You only lost a little bit of water, but now your average kinetic energy is much less. Because these were pulling up the average kinetic energy, now you have an average kinetic energy of much less. It was 11.5 if you counted 2 25s, 15, 3 5s, and 3 10s, and 4 5s. Add those up, divide by 10, because you have 10 units of things that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, yeah. And down here you've lost 2, so you only have 8. Now you only have 65 here. Divided by 8, that gives you 8.1. So it actually dropped the temperature. Now, I've seen one of these in a picture. I've never actually had one. But a lot of times people who do hiking out west, they'll wear, sling over their shoulders, a canvas bag full of water. You think, canvas bag full of water? That doesn't sound like it would work, but it sort of does. You know, you probably have something. And what happens is there along, especially on hot days, a little bit of the water evaporates from the bag, and when they start to drink, the water is much cooler than the air temperature because of this. That water that has evaporated dropped the average kinetic energy, which dropped the temperature, so it tastes like cooler water. Whereas if you just had a canteen, after an hour or two, it's going to be at air temperature. You drink it, and you're drinking tepid water, and that's not particularly conducive. Okay, you don't really like drinking this tepid water. Actually, I don't mind it, but a lot of people like the water cold, cooler, and that will make the water cool with no ice involved at all. Of course, you better have plenty of source because it will evaporate away as well as you drinking it. So that's what's happening with evaporation and condensation. Anytime you're evaporating water, you're just from a pan, you're actually dropping the temperature. temperature a little bit because the average kinetic energy is less. Okay. Now, they show a woman with a solar clothes dryer. Have y'all ever used a solar energy clothes dryer? I bet your mom or your grandma did somewhere in their past. It's hanging it out on the line. Okay, never mind. It's sort of a joke. Never mind. Any of you ever seen anyone hanging clothes out on the line? Yeah, that's what I was calling that. What's happening there? Several things are. Number one, the water evaporates away, especially if there's much of a wind, and especially if it's a sunny day, it goes even faster. Hot day, even faster. Even in the wintertime, it takes a lot longer, but you will do it. So there's a little blurb on that. Then there's I think a fairly weak concept supplied. Why is it called a pop can? Well, we don't call it pop cans. We call it a Coke can. Never mind. But anyway, it's worth a read. I think you'll find it interesting. But we're ready for 4.5, which is the next major section in this chapter. Only a couple left now, so we're getting near the end of this one. Let's talk about thermodynamics. Okay? Basically, a definition is the study of heat and its relationship to mechanical or other forms of energy. That's a fairly reasonable definition. If you look at the word, thermo means heat, sometimes temperature, but this time it means heat. So it's a study of heat. Dynamics means, as opposed to statics, dynamics would be changing. Okay? Statics, there's actually courses that engineers take. They're like physics courses, but they're more engineering. Statics and dynamics. Okay? Statics is steady state systems. Dynamics are changing systems. Okay? So this is a changing system. Your heat is being exchanged. The study of heat and its relationship, mechanical and other forms of energy, so it's changing back and forth one way or another. So thermodynamic analysis will include the system that you're studying or dealing with, the surroundings of that system, that's everything other than the system, and it also deals with all the internal energy of the system and maybe the surroundings as well. So what is your internal energy? That's total internal potential energy, but also total internal kinetic energy of the objects in question. The kinetic energy basically is something that would be resulting from temperature change. The changing internal potential energy may involve phase changes as well. Okay? So, here's some examples. Energy conversions, changing from one to another. Thermodynamics. Friction. What happens when you rub your hands together? They get hot. Okay? What happens when the brake drum hits the brake pads? They get hot. Okay? The friction converts mechanical energy into heat energy. I keep saying heat energy. Heat is a transfer of energy, so it changes it into heat that's being transferred. Okay? Now your heat engines. Anyone think of a heat engine? Y'all should think of a heat engine.
Locomotive?
Yes! Well, yeah. Any internal combustion engine is a heat engine. Devices that convert heat into mechanical energy. Is that what's happening in a car? Yeah, you have an explosion where stored chemical energy in the fuel expands rapidly because of heat, an explosion, and that forces down the piston, and the piston turns the drive shaft, so you're changing that to mechanical energy. So that's a heat engine. A locomotive engine, all those things are locomotive engines. The old ones were external combustion engines because the boiler was outside, but now even locomotive engines are internal combustion engines. Okay, so any heat engine is experiences heat conversions, energy conversions. Other applications: a heat pump. Okay, what in the list is a heat pump also related to? that list there, what thing is most closely related to a heat pump? A refrigerator. A heat pump you think of as heating, but basically a heat pump is the same as a refrigeration unit, just done backwards. Okay. Okay, y'all do air conditioning, refrigeration in the park, right? What are the components and processes going on there? That's light refrigeration. Okay. What's going on? What's the first thing that happens? Or one of the first things? Don't you have a compressor? And what's that compressor doing? You're using mechanical energy to compress a gas, what do we call it? Usually a refrigerant. You know, it used to be Freon, now they have different names for it, or something another. Refrigeration gas, okay? You're compressing it. What happens when you compress it?
It's going to vapor.
Say again?
It's a vapor.
What?
It's a vapor.
No, okay, it was a gas, you compress it, it becomes a, what happens to that gas? Say again? Okay, does it actually in your unit? Does it actually become a liquid? It may, I don't know. But what I know is it gets hot. You compress anything, it gets hot, because you've got this total energy that's in there. Compress it now the molecules are bumping into each other much more energetically because they're closer to each other. And the friction of those things, that produces heat. So that's the first thing. You compress it, produces heat. If your idea is to condition, the air condition, then you take your unit and blow air across it. So you're blowing that heat off. And then you do what? Let that gas expand in the condenser, usually you call it, don't you? When it expands then, it does a reverse. It cools off. And then you blow air across that unit into the car. And that's what's happening. That's an air conditioning. That's what refrigerators do. They just do it a little more succinctly, okay? Well, what a heat pump is when you compress the air and it heats up, you pump that into the house. And the condenser, you let that go to the outside, you know. And so a heat pump is just an air conditioner in reverse, basically. That's oversimplified. Okay, others, organisms. Guess what? We convert chemical energy in the food I ate for lunch today, including the apple I had right at the end. I'm converting that to heat right now. Guess what? I have a temperature of about 98.6, right? That's considerably warmer than room temperature. Way warmer. Room temperature is 72. Okay? I'm combusting fuel right now. As long as I got a temperature, I'm combusting fuel. I'm a little heat pump. Okay? I'm a little heat pump. Okay, so organisms, including microorganisms. They are heat pumps, okay? Or thermodynamic devices, okay? I don't know if you've ever thought about it. A hurricane is an energy converter. Because hurricanes originate where?
The ocean.
Okay, where in the ocean? The Arctic Ocean? Antarctic Ocean? Where do they originate?
Atlantic Ocean.
Say again?
The Atlantic Ocean.
Okay, the ones we know about do. What part of the Atlantic Ocean? Ever watch where they come from? Any little flood back here. This season, when it's hurricane season, that usually starts around June 1st and goes through much more active later in the season. But you'll see just about all of them start right in here. Off the coast of Africa, right around the equator. Those north of the equator make their way up here. South of the equator make that. We don't ever hear about those because we don't live down there. But if you watch them, they always come across like this. Now, some of them actually originate in the Caribbean or the Gulf of Mexico. Because again, it's really warm water there. But that's where it starts. Okay? And then they come now. because of their spin, and hurricanes always spin, say that way, northern hemisphere hurricanes always spin the same direction, counterclockwise. That's because they're low pressure, so air goes down, but the spinning of the earth gives it that counterclockwise spin. Okay? And always, if a hurricane is heading in toward shore, because of the counterclockwise spin, the east side of that hurricane is going to get the real drubbing, because the motion of the hurricane plus the spin of it, that's where the wind's worst. The west side, the hurricane's moving this way, but the wind's moving that way, so the wind is not as bad. Okay, so you don't want to be on the east side of the eye. Okay, you don't want to be right on the eye either. You'd rather be on the west side. And far on the west side if you can help it, but you usually can't. Well, what do? They always, because of that spin, they tend to curve up. If you ever watch the path, they curve up. Always. Occasionally they straighten out and straighten out and head in, but most of the time they're curving upward. And what they're doing is nature's way of dissipating the high intensity heat that's down here near the equator and moving it up here. If it didn't do that, the northern part here, probably all of Canada, even the northern U.S., would be so cold it could hardly support life, and they'd be burning up down here so hot that it's unbearable to do. So actually what it is the world's air conditioning system. That's why a hurricane basically turns out to be. So that's why they include them on thermodynamic. It's moving heat around, okay? Stars are heat engines, big time. I mean, they've got thermonuclear reactions going on every star that's an active star that's going on right now. Black holes are the remnants, and we don't know what's going on then, but it's sucking in energy like crazy. So again, thermodynamics. Energy is being transferred. Virtually any system that has any kind of energy input or output is thermodynamics in action. Okay? Most people would say there's 3 laws of thermodynamics. Okay? Our book's only going to deal with 2 of them. I'll mention the third one. Some books will actually say there's 4 laws of thermodynamics, but the 4th law, they don't name the 4th law, they make it the 0th law because they really needed that law for the first 3 to work. Okay? But we won't get into that either. It's a fairly simple law, but it's there. Okay, so the first law of thermodynamics is basically your conservation of energy. The components are internal energy, that's what's inside the material. Heat, that's something you're doing externally to either heat it up or to remove heat from it. Or work. And work is what's being done by that device or being done to the device, whichever it happens to be. So you have those 3 components. Okay, the internal energy was what was there to begin with and what's going to be there sometime later. It may change. You have heat that could be input or lost, and you have work, which you could be doing to the environment or the environment doing to you. In together. All 3 of these things can go both ways, positive or negative. Now, it's stated in terms of changes in internal energy. So we always refer to it in changes of internal energy. Now, I'm trying to recall exactly which this book uses. We'll get to that in a minute. And one application, all your heat engines, your internal combustion engine, that is basically a study in the first law of thermodynamics. Okay? Because what you're doing when you ignite that fuel, okay, you are changing the internal energy, and that's creating a whole lot of heat, but you're doing work. Because that's what your car engine is doing. It's moving you down the road, okay? If you're sitting still, then you're just creating a lot of heat, wasted heat, okay? Now, here is somewhat of an example of this. I'm not sure that anyone just looking at it would see what they're talking about here, because I know what they're trying to talk about. I see what they're saying. Okay. Here we have a cylinder, not unlike, but not the same as the cylinder you have in your car, with a piston. That's the top of it. Now, what you've done here is this cylinder was filled with air, right? Okay, air molecules there. The piston up here at the top. You put a weight on it, and what that weight does is compress the air down here. So now the molecules have forced to be closer and closer together because you have this weight on it, okay? So now the air molecules are probably heating up just a little bit, not very noticeably, but they are heating up some. Then you get a Bunsen burner and put under it, so you heat them up more. What happens now is they force that weight back up where it was to begin with. So the same work that the weight did pushing down, compressing these molecules, the Bunsen burner is using heat to force the weight back up. So you see you had some inherent internal energy of the system, okay? When you added heat, you did work on the system by raising the weight, okay? That's an internal, and that's what your car engines do. Your combustion inside the cylinder is not something external, but inside, forces the piston up, and that turns the drive shaft, and that gets you going down the road. Okay? Now here's a bigger scale picture of what you could have. This could be the same thing. You have a high temperature region, which would be inside the piston, right, when you have combusted the material. And some of that produces work, turning the drive shaft, sending you down the road. This is all a heat engine. But some of that heat that happens from here, not all of it does work. You have a low temperature region that's not cool, but it's unused. And that's what goes out the exhaust. And not many of you want to touch the exhaust pipe or the catalytic converter or the muffler or anything else like that when it's been running for a while, because you've got a lot of wasted heat that is being lost there. So that low temperature is lower than the inside of the thing, but this is why internal combustion engines are pretty inefficient. That's the only part that's doing work. Some of it is just going to the low temperature region to be dissipated into the environment. Oh, that was on the previous slide. Okay? The surroundings. Now, they blah, blah, blah about all this, but they haven't given you the formula. So let me go back. I should have done that right at the beginning. I thought they were going to show it, but they don't. It's in your text as equation 4.7. Okay? And they use some weird nomenclature. I'll use the same one they do, but I'll explain what they mean. JQ minus W is equal to U2 minus U1. The U's over here are the internal energy. That's internal energy. That's your internal energy. The heat is the JQ. Q we recognize, that's what we measure heat. But Q is usually measured in calories. Work and internal energy is usually measured in joules. So that's what the J is the joule equivalent of heat. So that gets it to the same units. And then W is the work. So if you're combusting something, burning something, doing whatever you're doing here, adding heat here, but you're also doing work with that heat, so subtract off that energy there, that creates the difference, a change of internal energy. If this was a super efficient system, then the U1 and U2 are really close to each other. Most of the time they're not all that super efficient. So you do have a change of internal energy. Okay? So this shows the relationship between these three components. Change of internal energy, and they said here, stated in terms of change of internal energy, U2 minus U1. U2 is final, U1 is the original. You added heat, you did work, that gives you, and the difference between those is you change your internal energy. Okay? All right. 115. Okay. All right. And we already showed these pictures. So I did think we needed to show that one. Now let me go back and also give you another one. If you have no change of internal energy, that's kind of hard to do, but it can be done. In other words, you're at steady state situations that your internal energy is not changing, then this could be 0 is equal to JQ minus W. Okay? Now, add W to both sides and rearrange it and say W is equal to, now, they do something weird here, JQ, but now they make a change of Q. Q high minus Q low. In other words, your high energy section minus your low energy section. Now you remember, I'll flick around to it. This one. Here's your Q high, there's your Q low. This they're assuming is a steady state system, which I don't see any real reason to make that assumption. But overall we'll assume that. Then the work that you get out of it is the difference between the high energy, high temperature region and the low temperature region. The difference there is the amount that does work. And this then is, this again is in calorie fuel equivalent of heat, makes it in fuels rather than calories. And that's how much work you're doing. So this equation represents this kind of a situation. All right. A lot of blah, blah, blah here. Okay. Let's go to the second law of thermodynamics. Now, this one's conservation of energy is fairly reasonably, I don't want to say easy or simple, but common to get your head around a little bit. Conservation of energy, we've talked about it in several different ways. Second law of thermodynamics is dealing with something that's even more difficult to express. There are 3 equivalent statements given here. All of them are true statements of the second law of thermodynamics, but none of them show the entire picture, because it's a really hard thing to do. Here's one way of stating it. No process can solely convert a quantity of heat to work. In other words, that system what we just had of your heat engine, high energy, low energy, and work's going out here, there's none that say this low energy is exactly like the environment, so therefore all that energy went to work. None of them. It can't happen. And that's what the first expression here. Second law of thermodynamics says, basically, you never can have a 100% efficient heat engine. Ever. No process can solely convert a quantity of heat to work. Okay? Second way you could express this. Heat never flows spontaneously from cold objects to hot objects. That doesn't sound like it's talking anything about this, but basically you're talking about a refrigerator then. Heat never flows spontaneously from a cold object to a hot object. You open the refrigerator door, I can hear my dad or someone saying, "Close the door, you're letting all the cold out." Well, you are letting cold air out, but you see heat doesn't flow from cold to hot. You're letting heat in, okay, which, cold air can come out. Heat never flows spontaneously from cold objects to hot objects, as in refrigeration. You have to force it to happen, okay? So here's the third way, and this gets back to this forcing thing. Natural processes tend toward a greater state of disorder. This is usually the one that's referred to with second law of thermodynamics. Surprisingly, these are all 3 really getting at the same thing. But natural processes tend toward a greater degree of disorder. And one example I like to give, think of your bedroom. If you don't do something, does it get neater and neater all the time? Probably not. Okay? Things just tend to disorder. If you don't clean up every now and then, soon things are a huge mess. Now that's on a very practical scale. Here's something that is probably maybe easier to wrap your head around. Let's say I went out and bought a deck of cards. And when you buy these deck of cards, usually, I think, I don't buy them frequently, but every one I think I can ever remember opening and looking at, we probably may have the order wrong, the ace of spades, the king of spades, the queen of spades, the jack of spades, the ten of spades, the down, all the spades, then you have all the hearts, then you have all the diamonds, then you have all the clubs, and they're in perfect order. So that's probably how they package them and quality control them and everything else. Okay? Right? So open the deck of cards and just throw them onto a sheet. Sheets lying on the floor. And by the way, they're all facing the same direction too. Throw them on a sheet on the floor. Get 4 people to take the sheet and just do this with them time after time after time. Well, first, when you throw them on the floor, are they in the same order they were in the box? No. And every time you throw them up, are they more likely to go back to that same order they were in the box? No way in the world. Everything, natural processes tend toward a greater state of disorder. Never the other way. If you're going to try to create order, you have to add energy to the system to make that happen. Your mom has to come in and clean the room or make you clean your room. It's got to happen that way. It never goes the other way. Another really, I think this may be on here somewhere, if you've ever spilled a container, dropped it to the floor and spilled it, okay? Have you ever unspilled something? You have. How?
Rewind.
Huh?
Rewind.
Red wine?
Empty wine.
Huh?
Empty wine.
Empty wine. I can't hear.
Hit rewind. Like on a video.
Oh, hit rewind.
Yeah.
Okay? No, you're adding energy. You're adding energy to the system because you can't just say, rewind. Does it? No. You have to add energy and make it rewind. No, you can never unspill something without doing a lot of energy and getting it back into a container. And you probably will never get it all either. Okay? So natural processes tend to a greater state of disorder. And that state of disorder is called entropy. The entropy always increases. The disorder always increases. Now, I hate to bring this one up because it may polarize people like crazy, but this is one of the biggest arguments that people have against the theory of evolution, is that the whole theory of evolution is that things are evolving into more structure. And that just doesn't seem to happen normally, okay? Normally, things go to more disorder. But that's a completely different subject, something to think about there. Okay, 2 reference scales. An object's external energy, that's the energy of global coherent motion, like I throw a baseball, okay? That's external energy, okay? It's associated with work. I did work to give the ball velocity, and it headed out and did whatever it did. That's one reference scale, the external energy. The other is the internal energy. That's the energy of the microscopic, often, in fact, always chaotic motion, incoherent motion. That's the cards bouncing around there. There's no order. That's all chaos, okay? They get more and more chaotic. You'll never ever get them all to face the same direction, much less be in the right order. Nothing, ever, okay? This is all associated with heat. The internal energy changes usually are accompanied by heat. It may be in the form of work or something else, or external heat or removing heat, but there's always that, okay? So there's the second law. Let's look at each of those processes individually. The first statement, conservation of energy, the heat engine. That's what we use for the first law. Now, you input some energy, and you output some energy. Okay? The efficiency of a heat engine is the work done per unit input energy. Okay? The second law states, now this is all first law, okay? It assumes input energy equals output energy. Okay? Remember our levers, input equal output. That's usually what we dealt with. However, you have to account for every bit of the output, and all the input as well. And the work is what the useful output is. The second law says efficiency will never equal 1. The work done is never the same as the total input energy. Ever. Ever. Okay? There's always some loss, usually to heat. Uncontrollable, unusable heat. Some energy is always degraded, and usually to heat. Okay? Think about your car going down the road. Okay? Sure, your internal energy is providing the work to turn the wheels to move your car down the road. But think about how much heat is going out of that exhaust pipe. Think of how much heat is going out of the radiator as it's cooling the engine. And think about how much, and this isn't as significant, but as your car is encountering molecules of air, it's producing heat. Think of the heat of the tires on the road, the friction heat. You felt of a tire after you've been on a long trip, it's pretty hot itself. Your brakes are hot, the water's hot, the exhaust pipe's hot. You've lost some heat, degraded heat that you'll never get the use for, okay? Ever, okay? Now, the formula we had before, we're leaving off that joule equivalent of heat, just count this as heat in the same units as work, joules or calories or whatever. Just have them in the same unit. What you put into the system, that's the hot side, is equal to the work you get out plus what's on the low side. And that's that same illustration we had before. Your efficiency, here's how you define it, is the work per unit input. Work done per unit input. And since there's always a QL, there's never 0 QL. If there was 0 QL, then this would be 1. Never happens. There's always heat loss. Always heat loss. Never without it. Okay? Here's the second statement. Okay? Now, the first statement, they could have gone back to the picture. You heat things up, work goes out, but you always have some excess heat down here too. It's lower than that, but the difference sum of this and this, that's what we just saw. This is going the other way. This time you're doing work to the system, like your compressor and the refrigeration, your air conditioning system. You're doing work to the system. That's your input, that work you did compressing there. Okay? It's going to produce some high temperature here, and it's sucking up air from here. If you had this contained, it would be heating that air. The work you're doing is heating that, moving it to the high temperature region. Now you try to blow that off and heat the room. Now you've got it in heat pump mode. You try to do that. Guess what? There's wasted heat here too. Okay? You'll never get all the heat out of this equal to the work that you put in. Work is required to move the energy from the cold region to the hot region. It never moves that way on its own. You've got to do work to make it happen. Okay? Energy arriving at the high temperature region is equal to the energy from the load plus the work needed to move it. Upgrading of energy by a heat pump is accompanied by greater degradation of energy somewhere else. Back here to produce the work, generally. Okay? That to me is a pretty obscure illustration of it. Here's the third statement. And this is the one that did the unspilling. Real processes are always irreversible processes. Okay? The measure of disorder is the entropy, and that always increases. Second law in those terms, the total entropy of the universe is continually increasing, meaning the order is decreasing. Okay? Now, that has some interesting implication if you think of it. We'll come back and think of it in a minute. Let's look at different ways to express it. Natural processes degrade coherent useful energy. That work you're putting in, whatever it is, natural processes do nothing but degrade those. The available energy in the universe is diminishing. That's sort of a scary thought, isn't it? The total available energy of the universe is diminishing because the universe is moving toward disorder. Entropy is increasing. Okay? That then, at least to me, makes you think, what was the Big Bang anyway? That's where all the energy came from. What initiated it? For our second law of thermodynamics to work, you had to have some sort of energy input to get it all started. Because this is indicating that we're winding down, and eventually we'll have heat death of the universe. Everything goes to that low-level heat that you can't get any usefulness out of. Strange thought. Direction of natural processes always toward disorder, entropy increasing. And this is their example. Spilled milk will never unspill back into the glass, even if you hit rewind. Never. It's not going to happen. Okay. All right. You can. Okay. I think I know what you're talking. You can make it look that way. Okay, I got what you're meaning. All right. Now, as I said, there are 3 laws of thermodynamics. Some people say 4. Let me give you what the third law is, which is not mentioned here, and not really needed here. But the third law is absolute zero may be approached, but can never be reached. Remember, we talked about absolute zero in the first part. That's on the Kelvin scale. 0 on the Kelvin scale, you can never get there, ever. You can get close to it, you can never reach it. That's theoretically true. No one has ever gotten there, but how you can't prove you can't go out of it. Actually, they sort of can't. Now, in the old days, when this was first developed, they thought absolute zero where all motion stopped. All the molecules quit vibrating, all stop. And they said that just can't happen. Okay. Well, with the advent of quantum mechanics, they say that's an impossible situation. What they're saying is everything goes to its lowest energy level. Even at the lowest energy level, there's still motion, okay, because there's energy there. But everything can't go to this lowest energy level at the same time. So the lowest energy level can be approached but never reached. It's saying the same thing. So that's the third law of thermodynamics. Now the 0th law is basically the law of thermometry. And it's a real simple one. If object A is in thermal equilibrium with, let's see, is this how it goes? Something like this. In equilibrium with object B, and if object B is thermally in equilibrium with object C, then object A is thermally in equilibrium with object C. Okay, that's it. And basically, it's how you do thermometry and everything else. You never, we talked about this before, you never really measure the temperature of something. You measure that temperature's effect on something else. Like, do you make the liquid expand? Do you make gas expand? Do you make the electrical resistance change? Do you make what? You're doing something to make something else happen. But even with a thermometer, which you're really changing something else, if you put the thermometer under your tongue, then the heat from under your tongue heats the glass heats the mercury in the thermometer and makes it expand. Well, there you have object A, object B, object C. Yeah. And if these two are in thermal equilibrium with each other, these two are too. So that's basic law, the 0th law of thermodynamics. Basic for all 3 of the previous other laws, but it actually should have come first. But everybody just assumed that was true. They didn't name it as a law. Now, there is an interesting little blurb at the bottom of page 108 not all their mistakes and misunderstandings, I think, are all that insightful. This one is sort of like that. Can something make its own fuel? You can make that a little bit, but you can never make it all. It never is going to be efficient. The second law says it won't. The regenerative braking in your hybrid cars, that comes close to recreating fuel because you're recreating electrical energy that later you can use to propel the car again, as opposed to heat that you never can use again. But even that has some heat loss. Always there's loss. You never can get it all back. So that was that one. It makes its own fuel. At the top of page 109 is, I mentioned him before, Count Rumford, Benjamin Thompson. A really brilliant engineer. Notice his years of his existence, 1753 to 1814. If you think about that, and he lived in, I believe it was, he was born in Woburn, Massachusetts, okay? He became a schoolmaster. There's a lot of interesting things about him, but his first activities seem to have been political. Because in 1753, we were the colonies. It was the Massachusetts Bay Colony. Alabama was a territory. We weren't even a colony. Georgia, I can't remember if Georgia, I think Georgia became a colony around 1735 or something. So all the 13 colonies were there. Massachusetts Bay Colony had been there for probably 100 or two so years. But he was a British citizen. He considered themselves a British citizen, and most of the colonists were. They all were, well, if they were citizens, they were British citizens. But when we had the War of Independence, the Revolutionary War, he said, no, I don't believe this. I want to stay a British citizen. And like I said, I don't know if this goes into it, there are actually some accounts that make you think he remained loyal to the British Crown and acted as some sort of a secret agent. And there's some suggestion that he may have colluded with Benedict Arnold, who was the notorious spy, who I think was hanged. Okay, Thompson escaped. He went back to England. They rewarded him by giving him a position, a count. But he was an engineer by training and interest, so he did the experiment with boring the cannon hole. Okay? Good potential paper topic. Okay? However, this cannot be your source. You have to get a source outside the book, not inside the book. Okay? This can give you ideas. You'll have to get a source outside the book. Okay? I bring that up because this, of course, one of my best classes, right, has 3 papers turned in so far. Just 3 out of 22 students.
Those 3, they do pretty good on theirs?
Oh, of course. Yeah, the early ones always do pretty good, right? The later you, never mind. I'll let you decide that. Okay. Before we end, let's go back here. I forgot there is one example, the last example in the chapter they put on the very last page on heat engines, or on thermodynamics. A heat engine operates with 65.0 kilocalories of heat supplied. 65.0 kilocalories of heat applied. What would you name that in terms of our symbology? In fact, this one right here, what would be heat applied? What stands for heat? What symbol do we use for heat? Q, okay? And you're applying the heat, so which Q would that be? Say again? Which of these Q's? You see 2 Q's there?
The L.
No, actually QH. You're applying that, okay? QL is leftover, okay? The low energy. So this is our QH. You got me saying it now. This is our QH. Is that capital H? I think it was, wasn't it? Yeah. Okay. Good deal. Thank you. Okay. Let me read on. Exhaust, 40 kilocalories of heat. 40.0 kilocalories of heat. This would be the heat in the exhaust. What would that be? Now it's your turn.
That would be L.
Yeah, that's your QL. Exactly. Okay? How much work did the heat engine do? What you reckon work is? Say again? Capital W, exactly. So what would be your work? Any idea?
You divide that.
Not divide it.
Multiply.
Not multiply. These are added, so you would subtract the QL from QH, and what would you get?
25.
Really? What'd you say?
You said subtract, didn't you?
Huh?
You said subtract.
Yeah, and what'd you say?
25.
Oh, 25. I thought you said 45. Sorry, I don't hear well. 25.0 kilocalories. That would be the work done. Okay? Now, what they didn't ask, and I will ask you. Now, they don't leave it there, because usually we don't measure work in calories. We measure work in what units? Joules. So how do we get from kilocalories to, say, kilojoules? I mentioned it shows up in so many of our tables. Let me see if I can run back and find that somewhere. Well, I'm not seeing it here. It's on the tables. There it is. Mechanical equivalence. What does it say? Very bottom. See it? Last thing on the slide. 4.184 joules is 1 calorie. So go back to where we were. Okay. So this is calories. And what do we just say? 4.184 joules is 1 calorie. Okay? Here we're dealing with kilocalories. So the easiest thing to do is make that 1,000 and make that 1,000. They like to go through and move your decimal. Just make them both kilos. Okay? So we have 25 kilocalories of work, but we want that in terms of joules, so we'll multiply by our conversion factor to get this in terms of joules. So we always put the units in their place. This blank is for the numbers, this blank is for the units. Always deal with the units first. Put the units in their place. What unit will go where to convert kilocalories to joules? One of those two units goes on top, one goes on bottom. Which goes where? Help me help. I'm going to go from kilocalories to joules. One unit will go on top, one will go on bottom. Which goes where?
Kilocalories on bottom.
Kilocalories have to go on bottom. That puts joules on top. Now you match the number with the units. And there we have the numbers up there. Which one goes where?
One on the bottom.
Yeah, I'm going to put the kilojoules, sorry. 1 in the bottom, because that's where kilocalories go, and 4.184 kilojoules goes on top. And now you multiply numerators, divide by the denominator. Denominator's 1, so nothing to divide by. 25 times 4.184. Anyone got a calculator?
104.66.
Say that one more time. 104? Is that what you said?
Yes, sir.
Point what?
600 joule.
0.600 something another. Okay, now look, we only have 3 significant digits there, there, and there. So let's leave this to 3. Let's round that to 105 kilojoules. Now, I bet you they do. No, they ultimately get to that. Okay? Okay. Now, I was going to ask you one more question that they didn't include here. What's the efficiency of that heat engine? Remember what efficiency is? Say again? Not too good. That's one qualitative expression of it, not very quantitative though. So what would be the quantity of the efficiency? Well, efficiency is work per unit input, and your input was your QH. And that would be 25.0 kilocalories over 65.0 kilocalories. Now here, definitely don't use the kilojoules. You can't mix your units. So use the work and measured in kilocalories. Someone do that on a calculator and see what you get. 25 divided by 65. Second? Okay, so that's about 38%. 38.4% efficient. Not very impressive. Probably better than most automobiles, unfortunately, but not very impressive. But about normal, I would guess. Okay, then there's the thermodynamics and action concepts applied. Actually a pretty interesting little thing to do. However, they say obtain an electric blender and a thermometer. This already begins to sound like you could have a disaster on your hand. If that's a mercury thermometer, do not use Mama's pots or its blender or anything else, because if you wind up breaking something, you're going to have mercury contamination, and none of that stuff can be used again safely. Okay? So you might want to read through this and think of it. Maybe use a thermometer that has colored alcohol rather than, because you don't want, this is saying put the thermometer in while the blender is blending. There's a real good chance you're going to break something. You know, so, but read it, see what it says. That ends the chapter, and I say this on every chapter, I'll say it again. Nothing replaces reading the chapter. Oh yeah, okay. Now, once you've read it, maybe a time or two, then look at the summary, and that will give you a lot of insight into what they consider the most important features. Okay? They can't go over everything here. Now, in this chapter, they italicize a lot of the important words, and you'll notice there's quite a few italicized words in there. Okay? You have a summary of equations, up to 8 equations. That's probably a few more than most chapters. You need to sort of keep hold of those. Key terms looks like maybe about normal or a few less than normal. Even though they give them alphabetically, they have page numbers where they're first located. Okay? And then the things I think would be most useful for studying for the test would be applying the concepts. All of these are multiple choice. Most of your tests will be multiple choice, not all. There'll probably be a few calculations, maybe 1 or 2 fill in the blank, but most of it is going to be multiple choice. So if you do these and then check your answers here at the end. Now, I haven't checked all these answers, but I hope by the time they've got to the 11th edition, they've got most of the errors out of it, but you'll have to see. If you can't figure out, if you think some of them are wrong, bring them to class and we'll talk about it. Then questions for thought. 17, that's probably about normal, maybe a little more than normal. And by the way, there are only 43 conceptual questions, or what do they call those? You're applying the concepts. That's maybe a few fewer than normal, but pretty close to normal. The 17 questions for thought, maybe a few more than normal. For further analysis, I think maybe a few more. There is an invitation to inquiry, which is sort of an interesting concept. You might want to read that. And then there's the Group A and Group B parallel exercises, 15 on each group, which is about normal to a little less than normal. If you got the big book, it has the answers in the back. I never found them in the small book. I don't know if they hid them away somewhere. I asked them to put them in there. I don't know if they got them there or not. Okay? Now, any questions? Chapter 4. Okay? We've already done all our labs that we have for Chapter 4, so there's nothing. Yes?
When will the next test be?
Okay, I said that earlier, and that's what I was just getting to, so let me answer it in this. Since we just finished Chapter 4, that means Tuesday will be the test on Chapter 4. Now, how will Tuesday run? Okay, time out on here. We're not going to do Chapter 5. If you got a big book with Chapter 5 in it, just skip that. It's a good chapter. I wish we had time to do it. We just don't have time. We only got a few weeks left. So what we got to do is hit on to Chapter 6. Electricity and magnetism, which I find far more useful for you guys than waves and sound. Even though waves and sound are important, I think electricity and magnetism, you have a lot more use for it. In fact, it may be just old hat for some of you, which will be a nice review. So we're moving on to Chapter 6. We're going to get started in Chapter 6 today, and like I said, we've only got 30 minutes left of what's normally our lecture time, and I don't think we'll get enough material covered in 30 minutes to have the first lab. So we're just going to go straight through and get as far as we can in Chapter 6, which the title of Chapter 6 is Electricity. In reality, it's electricity and magnetism. Just like the last chapter was heat and temperature, they named it that way. It was heat, temperature, and thermodynamics, so it was actually more. This says electricity, but it's electricity and magnetism. The first part of the chapter is electricity. The second part is magnetism, with some tying both of it together. Okay, so we're going to get started on this. We'll get just so far probably in this, and then we'll continue and do 2 more hours of Chapter 6 on Tuesday. When we finish those 2 hours, we'll have our first lab on Chapter 6. By then, we'll definitely be far enough along to have a lab. And then once we've got that 2-hour lab, and I don't think it'll take you 2 hours. I think you'll be through in well less than 2 hours. Then we'll have the test, the last 30 minutes or however long it takes you to do the test. And that will be on Chapter 4. So everybody understood? So therefore, I wanted to see if you have any questions on Chapter 4. Just outline for you good ways to study for that Chapter 4 test. Be ready for it the last 30 minutes on Tuesday. Okay, when we take a break, okay? Okay. So, and we're awfully close to that now, this ended Chapter 4. Any questions on it? Okay. Then what I'm going to do now is get out of this mode and go to Chapter 6. Not 5, but 6. Okay. It's going to take a while for it to boot up here, it looks like. Now, we're sitting at, what, 320 approximately? Yeah, 317. So we're not halfway through with our period, because we got started at 1:15, so we're only about 2 hours in, but this is a good break point. Do you want to break now, or you want to get started and then take a break a little bit later? It's up to you. It seems like I've noticed several people taking breaks already. That's fine. What about the rest of you? You want to break now, or you want to go on and get started on chapter? Break. Okay. Let me get this set up so it'll be ready to go when we do come back. I'll put this. Whoa! Okay. Turn on the booth. All right. Any questions on chapter 4? All right. As soon as the projector warms up, I should have hit that button before I did the other. We're doing chapter 6, and the title of it is electricity. And everything in the chapter does relate to electricity. However, magnetism is a big part of electricity. I don't know if you realize that or not, but we'll be seeing that as we progress in the chapter. So I think it should be called electricity and magnetism. That's actually how the chapter is broken down too. Core concept here, which is on page 140 if you got that open, electric and magnetic fields, here they are, the two of them, electric and magnetic fields interact and can produce forces. And they do produce forces, okay? They're called electrical forces. Now, we're not going to get hugely into fields, so we're going to talk about it some. And we're not going to go hugely into forces, though we're going to talk about them some too. We're going to deal a little more applied than the theoretical, but we will do a little bit of the theory as well. So let's start with the concepts of electricity. This is 6.1, and there is an overview which I'd suggest you read, but let's just talk about the concepts, okay? Now, for most of history, okay, electricity was neither understood nor dealt with very well. There was an ancient mystery, and people used to use it as a parlor game, basically, because no one knew what to do with it. It was just sort of a little thing. It's called the amber effect. People found out if they took a piece of wool. Now, y'all know what amber is? Amber is basically fossilized resin, like a tree, like a pine sap, or some sort of resin from some type of tree that has fossilized, and it's now an amber, clear-colored, somewhat clear, amber-colored material. And they found out if they rubbed that with fur and then held it over and touched somebody, it would shock them. And that's what they used it for, to play little parlor games, to shock people and stuff. That's about all they knew to do with it, too. That was all they knew about it. It was this interesting little phenomenon that you could shock people if you rubbed amber with fur. Later, they found out if you rubbed glass with silk, you could shock them too, but it was a different kind of shock that they didn't realize that. Okay? Now, for the longest time, no one knew what was going on there, nor did they care. It wasn't, like I said, very useful. There was a scientist named J.J. Thomson, probably no kin to William Thomson that we just talked about in the last chapter, but also Thomson with a P, as opposed to Lord Kelvin, who was William Thomson, I think it was. But anyway, different people. But J.J. Thomson identified these negatively charged objects as being electrons. Now, I'm not sure he gave them the negative charge, but he identified, well, actually, yeah, they had already decided what was going to be positive and what's negative, and then he discovered the electrons, that they were the ones carrying the negative charge. So if you go back then to the amber rubbing with fur, basically what you had there was the fur. When you rub the amber with fur, electrons from the fur went onto the amber, and then when I reached over and touched Hannah, she would get shocked, okay? So that was what was going on, okay? Now, the thing about the glass with silk, it was actually going the other way. The electrons were leaving the glass going to the silk, but she'd still get shocked because then it was pulling electrons off her, but they didn't know that at the time. Okay, so we do find charge carriers, electrons, okay? Now, this seems like a completely different slide here. Today, okay, the basic unit of matter is the atom, okay? That's at least for elements, okay? You might say the basic unit of matter for a compound would be a molecule. Both of those are arguably okay. But let's just stick with atoms for now, the basic unit for your elements, okay? An atom. Now here happens to be, and they don't tell you this, but it happens to be a helium nucleus, okay? 2 protons, 2 neutrons in the nucleus. Now, I don't know why the coloring's like this. I think I know, and the graphics people weren't doing a great job of that. If I were doing this, I wouldn't have any coloring around that. It'd just be total white. This would be the only colored part. So here's the nucleus here. it contains 2 protons and 2 neutrons. Now these contain almost the entire mass of that atom, that helium atom, concentrated in a tiny, if this were really to scale, that would be smaller than one of those little dashes, and the ring would be huge, okay? But they don't have the scale to do that. It's a tiny little nucleus that has almost the entire mass of the atom. And floating around it is a cloud, and I say cloud reservedly, only 2 electrons. They are just floating around there somewhere, 3-dimensionally floating around. They have almost no mass. Tiny amount of mass, but nothing compared to a proton and neutron. Okay? That's the helium atom. Okay? Now, the electrons are almost massless, incredibly tiny, but they carry a full negative charge. The protons are enormously massive compared to the electrons, and yet they carry just a single positive charge. So they have exactly the same amount of charge, they just have a whole lot more mass. Okay? The neutrons, on the other hand, how many hands do we have? Okay? Are actually more massive than either protons or electrons. Certainly electrons, they have almost no mass, but just slightly more mass than the protons, yet they have no charge at all. None. That's why they're neutron neutral. Okay? So, that's your setup. That is your basic unit of matter. This happens to be a helium atom. There's only one that's simpler than that, that's hydrogen. It's really simple. All the rest of them, like lithium, boron, carbon, oxygen, nitrogen, all those, they would be better represented by this thing. They have an inner cloud of electrons and then an outer cloud as well. This looks like this. For helium, you just have either just the inner cloud or just this, but not both, So that's what you got. Atoms are made up of electrons and nuclei. The nuclei contain positively charged protons, neutral neutrons, and basically all the mass. Almost the entire mass of the atom is concentrated on that tiny, tiny, tiny little nucleus. And most of the volume is occupied by these 2 floating around electrons that have almost no mass. A little amount, but like 1/10,000th the mass of a proton or a neutron. Okay, just really, really tiny. Now, Chapter 8 goes into this in more detail. Hopefully we'll get there before the end of the term. So let's look at the electric charge. This begins on page 141. And we've already mentioned where the charges live. The charges in matter are inseparable properties of the particles. You cannot have an electron that has not got a single negative charge. You can't have it. It's not an electron if it doesn't have it. It's inseparable. You can't separate the charge from the electron. Neither can you separate the charge from a proton. It's there. You can't say, oh, I'm going to take it out and then we won't have it. No, not. You might say, well, then what are the neutrons? If you notice that it's slightly more positive than the proton. Slightly more massive than the proton, but no charge at all. And here's a theory in quantum mechanics, okay, is that at some time in the way past, when there may have been some really massive interaction that went on, an electron was pressed into a proton, the negative charge, positive charge, they neutralized each other, and that's why a neutron is slightly more massive than a proton. So I don't know if that's been proven. I don't know how you could prove it, because neutrons are very hard to study. They're incredibly tiny. They don't live anywhere, or most of the time anywhere except in a nucleus, so they're hard to separate, and but it's the idea. It seems to support it. So the charges of matter are inseparable properties of those particles. Protons or electrons. Electrons are negatively charged, protons positively charged. Now, what's the charge interaction? Well, you know that story, don't you? Like charges repel each other. Unlike charges, attract each other. Okay? At least to our general understanding. Okay? Say if I had taken two pieces of amber and rubbed them both with fur, and then had them hanging from a string and brought them toward each other, they would try to go away from each other. Whereas if I had glass rubbed with silk and amber rubbed with fur and brought them close to each other, they try to go, because those are unlike charges. Unlike charges attract, like charges repel. Well, what's the attraction and repulsion? Those are forces, because things move toward or away from each other. Those provide the electric force. Now, of course, a single electron has very little charge, and it's incredibly tiny. A single proton doesn't exist very much anywhere, but if you had it, it's very tiny. So what we're talking about are massive numbers of either deficits or excess of electrons. Which leads back to here. Let me go back to here one more time and mention this. We said you could have either positive or negative charge, and then they're no longer atoms, they're called ions. Positive ion or negative ion. A positive ion, is that picked up a proton? No, you never move protons around. They're fixed in the nucleus, they're there, they don't move, okay? Is a negative charged ion the loss of a proton? No, okay? If you change the number of protons, you change the entire element. It's something completely different. It would require a nuclear reaction for that to occur. It doesn't happen. How you get positively or negatively charged objects is either gaining electrons or losing electrons. The electrons are the charge carrier. Sure, the protons have a charge, but they don't move. They stay where they are. It's the electrons that move. They can be rubbed off or rubbed on, but you don't change the protons, you only change the electrons. And that's what makes the charge, okay? So when you have these like charges, those are either excesses of electrons, they repel each other, or one excess and one deficit of electrons, and they attract each other. Okay, and then what I was saying before, an atom or a molecule that has a net charge, in other words, either excess electrons or deficit of electrons, a non-zero net charge, those are called ions. They're only from the loss or gain of electrons, not from ever changing the number of protons. That doesn't happen. It can't happen. You have to have a nuclear reaction for it to happen. So, this is a decent illustration. This happens to be a lithium atom, representing a lithium atom. Here in the middle, you have 3 protons. Okay, that's why I say lithium, because that's the only thing with 3 protons. Okay, now it has a bunch of neutrons in there too. I'm guessing at least 3, probably 3 on the nose. Okay, but they don't have any charge, so we're not showing. That's where all the mass is between those protons and neutrons. That's all the mass in that tiny and much smaller, tiny little nucleus. All the mass is there. And because it has 3 protons, it has 3 electrons. Now they've illustrated this properly. 2 are in what we call the inner shell, okay? And 1 is flying out there by itself in the next shell, the outer shell, okay? And what that indicates, and this will be next chapter more, that means lithium is very reactive. It's real easy for it to lose that electron, okay? Or it's easy for it to share that electron. So it's a very reactive. You don't find much elemental lithium out there. It's always combined with something. Now, I don't know the exact nature of it, but they call a lot of the new batteries lithium batteries. So I know it must have lithium in it. I don't know what the composition of that is. But that's a neutral lithium atom, or the representation of that. Now, as I just said, it's real easy for that lithium atom to lose an electron, because it's out there all by itself, it's farther from the nucleus, and if something comes along that really likes electrons, it's going to do it. Like if you rubbed it on glass, it would lose electrons and send it to the glass, or something like that, okay? So, if it did lose an electron, then this lithium is no longer a neutral atom. It's a lithium ion because it has a non-zero net charge. It has a net +1 charge. And that's the most common way that lithium probably exists as a positive ion. Single positive charge ion. Because it's real easy for it to lose that electron. Now this next thing is indicating something. It's just not realistic. This doesn't happen. It doesn't happen that lithium picks up an extra electron and become a negative ion. If it did, that would be fine, but it doesn't happen. Just take my word for it. It doesn't happen. But the principle is good. What they should show is probably fluorine. Fluorine has 7 protons in its nucleus, probably 7 neutrons too, somewhere there about, maybe 8, usually 7. It has 2 electrons in its inner shell, and then it has 5 electrons in the outer shell. It wants 6 there. It really wants to have 6 in the outer shell. Is it 6 or 8? Let me see. I don't want to be telling you something wrong. Yeah, it has 5. Okay, yeah, I thought I was right. It wants to have 6, but it only has 5. So therefore, it's going to grab an electron if it can. So fluorine, chlorine, bromine, iodine, they all do that. They all have 5 electrons in the outer shell. They want to have 6, so they grab them if they can. Okay? So lithium doesn't do this, but chlorine or fluorine would. It would grab an extra electron. And then it has 8 in it, or 6 in its outer shell. It's happy now. It is really, really happy. Okay? This doesn't exactly happen. But if it did, that would then be a negative ion. It has 1 extra electron that's not accounted for by the protons. So it has a net -1 charge. It's just lithium doesn't do that. Okay, sorry about that. And they were not meaning, they never said it's lithium, but that's what has 3 protons. Okay, did we get all that covered? I think we did. Okay, now let's talk about what I introduced things with, static electricity. Okay? I thought when I first looked at it, I said, oh, they've got a new figure in the book in this new edition that's better. It's actually worse. Okay? It shows what you would think would be a helium atom because it has 2 positive charges. Then it has 1 electron in the inner shell and 1 in the outer shell. That's not how helium does either, so ignore that one too. Okay? Now, let's move to static electricity. This is the next subtopic on page 142. It's what we were talking about, or I was talking about, when I mentioned rubbing amber with fur. That's what's happening. Electrostatic charge. A stationary charge is confined to an object. Okay? Now, we don't mess that much with electrostatics. They're there, it happens, but here's where you normally run into it. The old plastic seats that used to be on cars, sometime when you slid, say, cotton or polyester pants or shirt or something across that and reach for something that was metal, you could get a shock, right? Have you ever had that happen? Most of the seats are not covered with that anymore, but in the old days they were. I've been in cheap motels, when I was working on projects and stuff. They have some sort of cheap, probably polyester carpet or something. You walk along, shoving your shoe against that, you reach for the doorknob, and you shock yourself. Okay, that's static electricity. You've had it happen. You get clothes out of the dryer, and you have, what do they call that? Static clean. It's static electricity. The things have been flopping around there, one thing rubbing against the other, and then they cling to each other because one of them becomes positive charge, one negative charge, and then they stick. Okay? So, stationary charges confined to an object. The charging mechanism could be friction, rubbing the amber with fur. It could be contact with the charged object. Now, I don't know if any of you know that you've seen a Van der Graaf machine work. Okay, I don't know if you noticed in the lab when we're in that inner room down in 259, that thing over on the table over here that has a metal ball-looking thing on it. I don't know if you noticed. Someone bumped into it and it knocked it off with it. It's all right. That was a Van der Graaf machine. That one's not working. I would hesitate to even try to make it work. You're dealing with a large charge. I'm afraid it would shock somebody. But someone asked me if I wanted it, and I thought, well, just so people see what it looked like. But if you've ever seen one work, what they are, they have a belt that's running past the brushes, and that's picking up charges and depositing the charges on that metal sphere. Okay? And what they do before they start, they have someone stand on an insulating platform and place their hand on that, then they turn on the belt and start charging. And this works especially well with people with longer hair, or people with hair in general. That would help, okay? Not that funny. Okay, so, but with longer hair, and usually they'll pick some gal to do it, and she'll stand there and as they do, suddenly you see, and she doesn't realize it's happening, her hair starts standing up and just going in all directions, okay? Now, why is that happening? Because she's in contact with the metal sphere that is picking up all this charge from the belt, rubbing past the brushes. So something's getting charged, either positively or negatively, probably negatively, picking up electrons. So her hair is getting excess electrons, and those hairs are trying to get as far away as they can from each other because like charges repel each other. And then they bring it down, and the hair finally falls back into place, and they discharge it and let her step off. Now, she didn't want to step off while she was charged like that, because then she could have an arc and a spark, coming off the floor, and that could really hurt, okay? But that's contact with the charged object. She has her hand on the charged object, so she gets charged as well. Contact with the charged object. Now, there's another way you can get this, and that's called polarization. I think we have some illustrations, and I just thought of what one of these is, and I should have said that. I don't know if you've ever had a rubber brush and you comb your hair with it, and then you find out your hair gets more, a rubber comb your hair with it, and then you find out your hair gets wilder looking than it did in the first place. Now, when does this happen? Number one, you probably fairly recently washed your hair, and number two, it's been completely dry. It isn't at all wet anymore, and probably very low humidity in the air, like in the wintertime. That's when it's worse like this, because when you comb your hair with a rubber comb, it tends to pull the electrons off the hair onto the comb, okay? So then your hair winds up positively charged, and now it, just like on the Van der Graaf machine, tries to move farther away from each other. So you can't get your hair to lay down and do it actually looked better before you started brushing, okay, because it sort of is frizzing away. Now, what you can do with that comb, since it has extra negative charges, if you had on the table little pieces, scraps of paper, you could put the comb near the paper and pick up the paper with it, okay? And we'll see that in a little bit too. Now the paper becomes charged. Or, and this is the third one there, the comb has the negative charge, net negative charge. Little piece of paper is neutral, okay? Except that because it's negative charges, the charges in the paper, the positive charges tend to gravitate toward the comb. Negative charges try to get as far away as they can from the comb because it's negative charge. Like charges attract, unlike repel. So this becomes, the little piece of paper becomes polarized. Positive on one end, negative on the other. Well, it does it to the next little piece of paper, and they all form a chain of polarized things, and sometimes you can hold it next to, if the pieces of paper are small enough and your charge is large enough, you can pick up a whole string of them. And that actually, I've not ever managed to get it to do myself, but I've seen it done before. Now, We live in an old house. That's not really pertinent here, but it's what I'll blame it on. And in a lot of old houses, and new houses too, they have what they call cobwebs. What is a cobweb? Do you know? Is it from a cob spider that made it a cobweb? Nah, that's not it. It's not really a spider web, but it looks like a spider web. What it is, now here's another thing of nature. If you get a particle small enough, really, really small, the odds are it's slightly charged. One end of it may be positive, the other end negative. Just because it's so tiny, you have a break somewhere there, and an electron went this way or not that way or something like this. So things are charged. Very small particles. I usually call them colloids, C-O-L-L-O-I-D-S, colloids. They're extremely small particles, typically having a charge. Dust particles are typically like that. And if you have these charged dust particles, and one of them hangs on something in the ceiling, and then another one attaches to that, and another one to that, and another one to that, you have something that looks like a web. It's really not a web. It's a series of charged particles, colloids, charged dust particles, very small. And unfortunately, we have a few around our house, okay? We don't do enough dusting. We have very high ceilings, so you can see them hanging up there and say, oh, I don't have a broom. I don't have anything to get them down with. And they just hang there a little longer. Our niece came to visit us one time when she was quite young, and she said, y'all could have a nice haunted house if you wanted to. Shut up. Never mind. I didn't say that. Okay. So that's polarization. Let's see if we can show this. Now, these are way too big of pieces of paper. But if this was a tiny little piece of paper, very light and stuff, especially if you tore it and had jagged edges, then when you have that negatively charged poem, see negative, positive, negative, positive, negative, positive, negative, negative, net negative charge here, you hold it near the piece of paper, it's going to attract the positive charges and repel the negative charges, and now you've created a polarized piece of paper. It's neutral. The charge is negative. This is neutral. It still has the same number of protons, positive and negative charges, but they're just distributed differently. Reorientation induced without changing the net charge. And then if it's next to another piece, it's going to attract the positives up here and the negatives down here. And you have a string of them just like those colloids, those dust particles, those cobwebs. Okay? So that's what we mean by polarization. Not a net charge, but an induced charge. All right. And the static charge as you get from clothes in the dryer or wherever, they all sort of act that way. So let's look now, this is on the bottom of page 143, electrical conductors and insulators. These are important concepts because we'll be talking about them for a while. And a conductor is obviously something that conducts electricity well. What is the charge carrying electricity? A bunch of protons? No, they're charged particles, but you don't ever move protons. What moves? Electrons. Okay? So the electrons are free to move throughout the material. They're a good conductor. It has electrons that don't have to hang on to this atom. It doesn't connect you to a lithium atom or something else. It doesn't want to move anywhere. This is usually metals. And the metals have these clouds of electrons that are free to move from one atom to another with almost no interruption. They don't belong to this atom or that one. They're just free. They're a cloud. Okay? So, with the electrical conductor, if you add a charge to it, the charge goes all over the surface. Okay? For instance, that Van de Graaff machine, remember I said it was a metal sphere? As soon as it gets the charges off the brushes, then they attach to the sphere, and they go all over the sphere, equally, as far apart as they can, because they repel each other. So you put your hand on them, you start drawing them away. Okay? So metals are usually your best conductors. However, there is another material, graphite, which is pure carbon. And it's a very good conductor. It's not as good as some metals, but it's still a pretty good conductor. Now, what is graphite? Graphite is carbon that is bound together in two-dimensional array, so it has free electrons sticking out the other dimensions. And they are the ones that move. Okay. Graphite is pure carbon. Is there any graphite in the room that you know of?
Pencil.
Second?
Pencil.
Pencil lead. You're absolutely right. I had one up here at one point. Where is it? Did someone borrow my pencil? Because I know I had a pencil up here on the desk. It's okay if you borrowed it, but I just wondered, did someone borrow my pencil? Huh? Maybe it was from my first class and I didn't notice it, but usually I mark it in the book where we leave off. I know I had it here, but I do not see it anywhere. Okay, but graphite is the dark material in a pencil lead. Now, is a pencil lead all graphite? No, that would be way too soft. Okay, so they mix graphite with kaolin, which is a clay, but it's a fairly hard clay, and that's what makes pencil lead. And if you have a number 2 pencil, it has a fair amount of graphite and a fair amount of kaolin. However, if you have a number 1, which is softer, it has less kaolin, more graphite. A number 3 would have more kaolin, less graphite. Harder and harder. Okay, you make finer and finer lines. Okay, sort of beside the point. But that's what graphite. Something else that graphite is used for. Anyone know? Yeah. Second.
It's a lubricant.
Absolutely. Graphite, it's a lubricant. It is, again, two-dimensional sheets. Those sheets slide past each other very easily. So graphite, pure carbon graphite, is a lubricant. Now, something that's not quite graphite but awfully close to it, soot in your chimney, or something like that, you know, if you get that on your hand, it's pretty lubricating too. That's pretty close to being graphite. Two-dimensional, actually crystals of carbon, pure carbon. Okay, now electrical insulators would then be things without any free electrons. The electron motions are restricted. Usually these are great, big, bound molecules that don't let electrons flow around. And some of the things that and when you have these, usually the charge tends to remain on the object right where you put it, because there's not a lot of mobility in those electrons. So if you were to charge, I think what would be a good example, put a charge on something like a piece of ceramic or something, it just sits there. It doesn't move around. It doesn't distribute. Okay. Glass is a good insulator. Glass is a series of silica, that's silicon and oxygen units that are not they're not in a lattice, a very strong lattice. So they don't have any free electrons moving around. Wood, okay, that's an organic material made of complex carbohydrates, great big molecules without any spare electrons. Diamond is an excellent an insulator. Guess what? It's pure carbon too. Chemically is the same as graphite, but you couldn't be any further apart. Graphite's a good conductor, diamond's a good insulator. What's the difference? Diamond's a three-dimensional crystal structure. Those electrons are definitely bound. There's nothing free to move around. So that's what makes graphite a good conductor, diamond a great insulator. What's more, what's another characteristic of diamond? There's no natural substance known to man that I know of that is harder than diamond. I don't know if they've even created any substances that are. It's hard. It's a three-dimensional crystal. It will scratch anything. Anything, metal, whatever. In fact, what do they use to cut through reinforced concrete with rebar in it? The only thing that will cut through that, a diamond blade. It's not pure diamond. They just encrust diamonds on the edge of a steel blade, stick them to it, and that blade will cut through concrete, it'll cut through metal, it'll cut through anything else. The diamond's the hardest substance known. So there, it's an abrasive. So this form of carbon is a lubricant, this form of carbon is an abrasive. You can't get any further apart. This one is a conductor, that's a non-conductor. You can't get any further apart, and it's exactly the same chemical structure, chemical composition, just different structure. Two-dimensional crystal structure, three-dimensional crystal structure. Okay? Now, how do you get diamond? Compress other carbon under huge amounts of heat, huge amount of pressure, and you change the crystal structure from carbon to diamond. Okay? That happens in nature, and actually there was a lab at UAB campus that they made artificial diamonds by doing that, but it's not a way to make money because they can make only very small ones that you might use to crust the blade with, but you couldn't get any expensive diamonds out of that. It was expensive, but it was very expensive to do. And then we have something in between. Semiconductors, they conduct or insulate depending on the circumstances. It might be temperature, it might be direction of flow, it might be just about anything. Now, in the past, it didn't sound like much use for that until the advent of computers. And in the old days, to do electronics, you needed what we called vacuum tubes that had high amounts of charge on one part and another part, a lot of heat given off. They had to be at a vacuum, so they were tough to deal with. If you ever got a crack, they would blow or something like that. They were really messy, okay? And then they came out with transistors, which were much more efficient. And then they discovered semiconductors could do sort of the same thing. It's not quite the same that transistors did, but even better, okay? So now computer chips, solar cells, all sorts of things like that have semiconductors, and that's what does a lot of the work. Electric charges flow one direction but not another, things like that. Now, it's related to, but not quite the same thing, as a diode. Y'all know what a diode is? What?
Allows electricity to flow
One direction, not the other. That's a lot similar to sort of semiconductors. It conducts or insulates depending on conditions. And y'all use them in your alternators, right? Dual diodes. Yeah. But that's not the same, but it's a similar kind of concept. Okay, moving on to, and there's a concept applied on static charge. Yeah, it has some pretty interesting thing you could do that with that, so you might try doing that one. I don't think it involves your mother's blender. Back on conductors. There is a table in the text. I thought it was going to show up in the slide. It didn't. Here is a table of some of your insulators conductors and insulators. And this table of electrical conductors is just about in the order of conductance. The very best electrical conductor is silver. Very best. We don't really use it that much. Why? Well, awfully expensive. Yeah, you couldn't afford it. But just behind silver, just slightly not quite as good, but almost as good, is copper. Copper is much cheaper. And it has some other advantages too. Silver is a pretty brittle metal. So if you had a piece of silver, it would be that. Copper is very, what's the name for it?
Malleable.
Ductile. Huh?
Malleable?
Malleable would be in sheets, ductile is in rods. Yeah, same type thing. And it's very easy. So you can put them in wires, and the wires bend easily and stuff like this. Especially if you put strands in there. It makes it much easier to do. Okay? So copper is than the one we use the most, though silver is a little bit, just a little bit better. Gold is a very good conductor, but it's pretty expensive too. It's very malleable, so it may or may not be good. Actually, you can just paint gold on gold leaf and maybe get some pretty good conductors that way. Aluminum's about the next best, and then your graphite, and then tungsten, iron, lead, nichrome. Nichrome is actually an alloy. If you look at that, it's nickel and chromium, which either one of them are probably sort of conductors, but together they make a pretty, they are conductors, but not good. Now, I bet you y'all have dealt with nichrome before, whether you realize it or not. Anyone know what it's made out of nichrome? Any of you ever use an electric range? Stovetop. Okay? That material there is nichrome. I think most of the time it is. Or in an oven, if it's an electric oven, that material that gets red, you send current through it, it's not a great conductor. It is a conductor, but then it heats up because there's a lot of resistance in it. That's what we use as heating elements. So I wouldn't be surprised if some of the heating elements that you might run into probably are nichrome. Maybe not exactly. So, how about tungsten? When do we use tungsten? Not so much anymore, but it used to be pretty popular. The filament in the light bulb. The original, the Thomas Edison one, I think was tungsten. I think they're still used. But guess what? We don't use that many incandescent bulbs anymore. We have a few at our house still, but not many. And when they blow out, we probably won't replace them with incandescent light bulbs. The ones we might are in chandeliers. I don't know if they have other types, but you know, what replaced a lot of incandescent bulbs were compact fluorescents. Okay? But now what's replacing them is LED. Okay, they're a little more expensive, but they last a long, long time. They don't get nearly as hot. They're much more efficient. You don't have a lot of heat loss. You have some, but not as much. So tungsten was used in that. Okay. Now, does that list seem just vaguely familiar? List of electrical conductors. It seems like we've seen some list that had silver and copper and aluminum and these other metals in it, almost in the same order. What was that? The last chapter.
Specific heat?
Heat conduction, not specific heat, conduction, conductivity of heat. And sure, and remember the things with the plugs in the thing, the little plug, and some will get hot, some conducted heat more faster than others. Okay, the reason what's conducting the heat was those free electrons. Okay, it wasn't the material themselves; it's the electrons in the material. They are what make a conductor a conductor. So it's no surprise they're the same. The lists are the same because the same. The heat carriers and the charge carriers are the same. It's just that electrons are themselves charged. They're not, you know, but they also their motion, their kinetic energy is what transmitted the heat. Okay, the insulators: rubber, glass, carbon, diamond carbon, as opposed to graphite carbon, plastics, and wood. Now, one thing they didn't mention there was ceramics, but rubber, you know, glass, these are good. Now, where do you see an example of these being used as insulators? Especially think ceramics, and to some extent glass. Say again? Power lines, exactly. What holds them off the pole and off of anything else is a ceramic thing there, and therefore it will not conduct the electricity. Even if it's wet, it doesn't. Whereas wood can get sort of saturated and it can conduct some electricity, but ceramics don't. Big, bulky molecules that don't transmit electrons at all. All right, good deal. Okay. I think we're ready for electric charge now. Now this slide set doesn't seem to be quite put together the same way your book is. Electric charge was a subtopic back on 142, but here we're measuring electric charges. So that's really what this is talking about. If they put measuring electric charge, it would match the book better, but they just say electric charge. Now, what would you say the most basic unit of charge would be in nature? Smallest unit of charge you could get. A single electron. That's absolutely true. A single electron. But guess what? Single electrons are very hard to detect or measure anything else at such a little charge. So that's a microscopic unit of charge, a single electron. Macroscopic, something we can measure, is the amount of charge equivalent to 6.24 times 10 to the 18 electrons. Now what do we mean by that? 6,240, 000, 000, 000, something like that number of electrons. I mean, huge number. I don't even know what prefix goes up to 10 to the 18. That's a Coulomb. Now, why is it a capital letter? Named after somebody. Charles Coulomb, I believe his name was, a French physicist. A lot of the early electrical research was done in France. That was the time of when France was sort of at its peak, culturally and all ways, academically. It was way up there just before the French Revolution, unfortunately, and shortly thereafter too. And that was about the time that Benjamin Franklin went over and was ambassador to France for a while. You can't convince me he didn't get together with some of these French physicists and compare notes, because he was pretty much of a good scientist himself. The Coulomb is the metric unit of charge. Okay? It's not the basic unit, that would be the electron, but a Coulomb is a macroscopic unit, which is 6 times 0.24 times 10 to the 18 electrons, that amount of charge. That's something we can measure. Okay? So, of course, the electron charge is in the basic one, the fundamental charge. You cannot get any less charge than there's in an electron, because that's the smallest you can get. Smallest seen in nature. The quantity of charge relates to the number of electrons that are floating around, okay, or exchanged or whatever. And we measure that in a bigger unit called a Coulomb. Okay. So here's the formula that relates charge to the number of electrons. The quantity of charge, remember I said this in the last chapter. Capital Q was the symbol for heat. Little q in this chapter is a symbol for charge. So don't get them confused. And this is a macroscopic unit measured in coulombs. And that's N times the electron charge. That's the smallest charge you can get. The basic charge in nature is the electron charge. You can't get any smaller than that. And how many of those you have multiplied, that gives you how many coulombs. That N would be 6.24 times 10 to the 18 to make that 1 coulomb. Okay? Anything less than that would be a fraction of a coulomb. Anything more than that would be a multiple of a coulomb. Okay? Make sense? Now, since this equation is true, Q in coulombs is equal to N times electron charge, then you can divide both sides by N. You know what N is. It's this number right here. 1 coulomb divided by that number of electrons, that will give you the electron charge, and that's 1.60 times 10 to the minus 19 coulombs per electron. A tiny fraction of a coulomb to electron. That would be 0.00000000000000016, or something like that. Some really tiny fraction of a coulomb is what a single electron charge is. You just take it, and rather than multiplying the number of the charge of an electron by that, you divide not 1 coulomb by that. You get how many coulombs per electron. Okay? And in the front of your book, especially if you have the big book, but if you have one of the small books, you'll probably find this table somewhere in the beginning or end, but you'll see on there physical constants. Fundamental charge, 1.60 times 10 to the minus 19 coulombs. Exactly the number you see there, that is 1 electron charge, also called the fundamental charge. Okay. Now, so therefore a proton, since it has the same charge but positive, a single proton would have exactly that charge, that many coulombs for a single proton, but it would be positive where the electron is negative. Okay. You would need to accumulate more than 6 billion electrons to get 1 coulomb. I mean, that is a tiny, tiny number. Okay. Let's do the example 6.1 that's on the bottom of page 141, top of page 144 to 145. So let me see if I can find. Okay, let's do it here. Combing your hair on a day with low humidity, remember that's required, because see, water can keep static stuff from happening. That's why in the dryer, when you dry out all the water, you get a lot of static electricity. So if you have a lot of humidity in the air, this won't work. But combing your hair on a day with low humidity, and your hair needs to be clean. The oils will also keep that from happening. Results in a comb with a negative charge on the order of 1 times 10 to the minus 8 coulombs. Oops. Now what symbol do we use for charge?
Little q.
Little q. So the little q here is 1.00. They put 3 significant digits and say on the order of this. So it's saying approximately this. Well, if it's approximately, it can't be that precise. But anyway, they're trying to get 3 digits. Times 10 to the minus 8 coulombs. Capital C coulomb. The word coulomb is spelled with a small c. It always sort of confusing me. If you named it after somebody, it thinks the unit, the name would be capitalized, whether you capitalize the symbol or not. But no, they write the name with a little c, but then capitalize the symbol. How many electrons were transferred from your hair to the comb? So Q is this, and Q is also equal to N times E. Remember? That was that first formula we had. Whoa, where was it? There it is. So Q is equal to N times E. Okay? So, the question said how many electrons. N is going to answer the question. N is what we're looking for here. Okay? So how do you get from Q is equal to NE? Isolate the N. What would that be? How do you do that? Divide both sides by E. Right. Okay? And you wipe out the E's here, and you get N is equal to Q over E, where E is the single electron charge. Well, you have 1.00 times 10 to the minus 8 coulombs, and E, as we saw from here, that E is 1.6 times 10 to the minus 19 coulombs per electron. 1.60 times 10 to the minus 19 coulombs per electron. Now when I do electron, the symbol for it, I usually put E with a minus by it. Now there's a mathematical reason for that. In mathematics, E by itself stands for an irrational number, probably the second most famous irrational number, the most famous being pi. You don't have square root 2 and things like that. But this is E, which is the base of our number system in the calculus sense. Okay? So I always like to put a minus sign by it, just so I don't think I'm writing the number E. That's the symbol E, electron. Okay? Charge of the electron. So, do any of you have a calculator and you know how to use the scientific notation in it? Anyone have a calculator? Okay. Do you know how to use scientific notation? Okay. I'll walk you through it. Now, the 1.00, you don't have to do that. You can just hit the number 1. And then, for scientific notation, don't do times 10 to the minus 8. That's a long way to do it. Look for a key that's either EE or EXP. Either one of those two keys. Do you see one? Okay, if you press that EE or EXP, you'll see another little block show up top, right? A superscript. That's where you type in the minus 8. But on that fancy calculator, do not use the negative that's used for subtraction. Use the minuses in parentheses. You see that one? So hit that minus in parentheses and the number 8. Then do your division key. That's over there with addition to that number. Divided by 1.6, you don't have to put the zeros. You go EE or EXP, and then do your, in that little block up there, do the minus in parentheses, that's the negation key, 19. And then press enter and see what you get. A pretty big number, right? What do you get? 6.25 times 10 to the what? 12 or 11? 10. 10 to the 10th. 10 to the 10th. Okay, and then you read it just in the reverse, of what you did. And the coulombs go out, and this would be equivalent to that many electrons. Combing your hair is going to move around 62.5 billion electrons. Yeah, electrons are very, very small. It doesn't take much to move that number around. Just comb your hair. Move that many, like 62.5 billion electrons. Okay. 6.25 times 10 to the 10th electrons. I like to put that extra little minus sign there to remind myself that's an electron, not something else. Okay. That's on electric charge and how you measure it. Now we're moving to the next subtopic, which is electrostatic forces. Okay? And Charles Coulomb did a lot more than just get a unit named after him. What he did to get that was come up with this law which shows the relationship giving the force between two charges. Okay? It's very similar in its format to that of Newton's law of gravitation. Now, do you remember what Newton's law of gravitation looks like? Now, this is not the acceleration due to gravity. This is actually the universal gravitational constant. The force due to gravity is some gravitational constant, G, capital G, not the little g, times the mass of one object times the mass of a second object divided by the distance between them squared. That's Newton's law of gravitation, where that capital G is a universal gravitational constant. That would be if you're talking about the force due to gravity between the sun and Jupiter, between Jupiter and one of its moons, between the Earth and Venus. Whatever it is, the universal gravitational constant would be true no matter if it's in a different solar system, a different galaxy. That's still true. At least we think it is. We've never been there to check. But then the mass of one times the mass of the other divided by the distance squared. Okay? Now, what then gives you Coulomb's law is fairly similar to that. And let's see if they're going to list it here. Yeah. I'm going to leave it up here because I managed not to get it in the way. The force due to electrostatic charge is some K, just like G, but a very different number. Q1 times Q2, the two different charges, whereas there is different masses. That's the gravitational is by mass. Q is by charge. divided by the distance between those charges squared, just like r was the distance between the masses. So, very similar format. Okay? A big difference, though, is that Q here is K here is 9.00 times 10 to the positive 9, and the units here are Newton meter squared per Coulomb squared. Okay? Certainly has to have Newton because the force is in Newtons, so that's what it's got to do. It's got to be times meter squared, so you cancel out this distance of meter squared, and divided by c squared, so it'll cancel out the c times c up here, c squared. Now, what they show in the next slide is the comparison of K versus G. Now, this is a very fair comparison because, number one, the gravitational field forces, usually you're dealing with huge, huge masses, okay, but also pretty large distances. So those kind of cancel each other out. But still, G is a, whereas charges are really tiny, you know. So you're dealing with usually 10 to the minus 8 coulombs or something like that most of the time. And the distances, so they're very small too, so they kind of cancel out. But so indeed, you can kind of look at the ratio between K and G. And let's see what it is. If you remember back, G was 6.67 times 10 to the negative 11 Newton. Now here they missed something here. That should be meter squared, okay, because it's in the denominator. Now let's see, I think in the book, do they have this in the book? I thought they did, but I don't see it. If you go back to when we studied Newton's law of gravity, you'll see that the G is Newton meter squared per kilogram squared, okay? They left that out. The typesetter messed it up. Let's see if I can find that. Well, I can't see it, but it's in here somewhere. All right. Oh, there. Well, no, not there. Okay. So what we're going to do is compare this, and this is Newton's law of gravitation. Now, they put the G up here in the numerator. It doesn't matter where you put it. And I already wrote this on the board. Oh, there it is. Force due to gravity is G times M1 times M2 divided by, I said R squared, they say D squared. So it's the distance between them. Okay? And remember, Coulomb's law was the force due to electrostatic force was K times Q1 times Q2 over D squared. So very, very similar. So let's look at except K was 10 to the positive 9, G is 10 to the minus 11. So when you look at that ratio, 9.00 times 10 to the 9th, positive 9, compared to G, which is 6.67 times 10 to the minus 11. Now, of course, there are different units in that place. Look at that ratio. K is bigger by tons. 1.4 times 10 to the 20th. That would be 1, 4, 0, comma 0, 0, 0, comma 0, 0, 0, comma 0, 0, 0. 6 pairs of sets of 3 zeros. Huge, huge. All right. So there's Coulomb's law. Okay, before we move on, let's do example 2. So I think I'll use this slide here. Oh, by the way, I'm actually late, am I not? I was supposed to call roll again at 3:45, and I forgot to. It's now almost 4:45, right? So I'm a little late, so I'll catch those people. Amber never made it in today. Okay. Bailey's still here. Josh is still here. Alexis didn't make it in today. Terrell is still here. Justin Hay didn't make it in today. Tef hasn't made it in yet today. Travis was here, but he was here at 3:45. He wasn't here at 4:45, so I'll mark him here. Shanika hasn't come back from her other class yet, so I'll leave that blank. Cole, he is, okay, all right. I thought he was still here. Okay. Brandon's still here. Gary didn't make it in today yet. Joseph's still here. Trey didn't make it in today. Coco is still here. JJ, was he here at 3:45? He still was? Yeah, he just recently left. Okay. So he's okay. Hannah is still here. Will is kind of here. Okay. Miranda's still here. Justin Struthers is still here. Lauren hasn't made it in today yet. And Courtney hasn't made it in today yet. I think a lot of people are blaming on the Honors and Awards Day that people just didn't show up today or whatever. So, let me clear this. I should have done that an hour ago, but I forgot it. Let's do example 6.2. Electrons carry a negative charge and revolve around the nucleus of an atom, right? Yeah, we know that. Which carries a positive electric charge from the proton. Okay? Sorry. The electron is held in orbit by the force of electrical attraction at a typical distance of 1.00 times 10 to the minus 10 meters. So this is our D in those formulas that we had. D is equal to 1.00 times 10 to the minus 10, was it? Yeah, minus 10 meters. Okay. What is the force of electrical attraction between the electron and the proton? So we're looking for the force. That force is K Q1 Q2 over D squared. We got the D. Know what that is. What is the charge on an electron? Anyone remember? Oh, and the K here we see right down there is 9.00 times 10 to the 9 Newton meter squared per Coulomb squared. Okay? And we multiply that by the charge on the electron. Anyone remember what that was? That exciting, huh? Okay, 1.60 times 10 to the minus 19, wasn't it? Coulombs? Okay. Charge on a proton, same thing. 1.60 times 10 to the minus 19 coulombs. Divided by D squared. Well, your D is 1.00. Whoops. Oh, my. 1.00 times 10 to the minus 10 meters. But you're going to square that. Okay? Big exercise in scientific notation here. Okay? Now, there's a couple ways you could go here. By the way, let's just look at our units first. This Coulomb squared is going to cancel out that Coulomb and that Coulomb. The meter squared will cancel out the meter squareds down here. You're still going to square the number, but not the unit. Okay? So, if you got your calculator, then it's 9 point, you can just say 9, EE or EXP 9, times, here's the easy way to do this one, 1.6, EE or EXP, your negative in parentheses, 19, close that and square it, because you see these two numbers are exactly the same. Okay? So if you have a parentheses around it, square that. I think you can just square it the way it is. Most calculators will do that without parentheses. Divided by 1, well, you can do this one in your head. This will be 1 times 10 to the minus 20. Okay? So it would be 1 EE or EXP, negative in parentheses, 20. And then press equal, see what you get. Have you gotten it yet? Oh. Say again. 2.30 times 10 to the negative 8, and the unit that's left is Newton. Now that seems like a very small number. That would be 23 billionths of a Newton, which seems pretty small, okay? Until you think about how small these electrons and protons and things are. It's a pretty big number compared to what they are. So, yeah, it's not unreasonable, and that's what they got in the book. Okay. So those, goodness, my throat's leaving me, are your electrostatic forces. Let's now move to the next subtopic, which is force fields. Okay? All right. Now, let's go back to this fact that electrostatic forces seem to be stronger than gravitational forces. Now, what reinforced that? Remember the story of combing your hair, if you had hair, with a rubber comb and getting it charged and then picking up little pieces of paper with it? Well, just guess what? The gravitational force is pulling down on those pieces of paper. This electrostatic force is overcoming that and picking them up. So in one sense, it is stronger than gravitational forces. Yeah, that's maybe not that much stronger, but still stronger. But, on the other hand, gravitational forces act over millions, I'd say billions of miles, whereas electrostatic forces have to be in close proximity. You can't hold that a meter above and pick up those things. You have to be right down at it. So the ranges are very, very different. Even though the electrostatic forces are stronger, the ranges are much different. Okay? So, let's move on to force fields. And what led me to this is, does it seem odd to you that gravitational forces, electric forces can act on objects that are not touching? In fact, that's typically what they act on most. You know, they will act on objects touching, but the electron flying around the proton, the nucleus, it's not touching the nucleus, and yet it's being pulled in by the nucleus. Just like Earth going around the sun is not touching the sun, but is kept in orbit by the sun. So how do these forces act through space without contact? I know when I hit the desk, I exert a force on it, and I push on the desk or whatever, you know, that's a contact force. How do these forces work? Well, this is a construct, kind of a model, but it seems to work. Charges are surrounded by what we think of as electric fields. What in the world are electric fields? They're vectors in nature, meaning they have direction to them. Okay? And they point in some direction. Okay? They're not things that are actually touching, but fields that surround them. The fields and the charges are completely inseparable. Just like fields and gravitational field and masses are completely inseparable. If you have a huge mass like the sun, the moon, the stars, you know, something like that, you know, Earth, the planet, whatever, it has a force field around, a gravitational force field. Anything within that field is going to be pulled toward it. Okay? Same thing with charges. If I have a charge up here, You want it to be positive or negative? I don't care. Positive. That means it has a deficit of electrons. So it has a positive charge. It has a force field around it that are going to be pulling negative charges toward it or pushing positive charges away from it without ever touching. Okay? So if you have the charges, you got the fields. If you have the fields, there's got to be a charge around there somewhere. Fields act on other charges, like I just said. That positive charge up here with the field around it are going to act on positive charges to push them away or negative charges to pull them to it. It's always going to happen. Okay? The direction of the field, now this is where we go with a little bit of arbitrary definition here. We say the direction of the field is the motion of a positive test charge if you put it in the field. So if this is a positive field here, if I put a little positive charge here, which way is it going to go? Yes, away from, exactly opposite from the charge here. So therefore, the field lines that we call them are always going to point away from a positive charge and toward a negative charge. Just remember that. You visualize this, now they really don't exist, with lines of force. Okay, and we're going to see some in just a minute. The same ideas apply to gravity and magnetism, with this exception. Gravity are always attractive forces, whereas field charges and magnetism are directional. They can be either toward or away. Okay? We'll get into that a little bit later, too. Okay? So here's what the rules are for force fields. If you had a negative charge here, we had a positive before, and you put a little test charge there, test charges don't head toward the negative charge you had, so the field lines would be pointing toward a negative charge. But if you had a positive charge here, put a little test charge there, it's pointing away from it. So the field lines always point toward a negative charge, away from a positive charge. The electric field lines point away from positive charges toward the negative charges. Okay? We'll go over these same type things with magnetism. With gravity, they always point toward the mass. Always. Always. Okay? I don't know what was supposed to be here, but nothing is showing up when I click. Okay, here's the picture of it. But before we go to this picture, the work of Michael Faraday, okay, and James Maxwell, okay, from Maxwell's equations in the early 1800s finally provided a new mental model for action at a distance, and that's these force fields. Okay, so there's a couple more people. If you haven't chosen a paper topic, we're going to run into lots of people you could. We've already talked about Coulomb. We've talked about Coulomb's law. We're going to talk about others. Here's Maxwell. Here's Faraday. There's tons of people we're going to be mentioning in this chapter and the next. Okay, if you haven't already chosen, if you want to write on somebody, there's lots of choices here. We had lots in the other chapters too, but maybe more here. So here's what we would do then. If this was a small positive charge here, now let's take this one out of the picture. If that's a small positive charge, then these lines are going to radiate from it. The force field lines are going to be going away from it because they always go away from positive charge. So that would be, making a three-dimensional porcupine. Okay, all the charges going away from it. Another positive charge will look the same way. But you start bringing these close to each other, the field lines. So here's a characteristic of field lines. Field lines can never cross. They can connect, but they can't cross. But if they connect, only if the arrows are pointing in different directions. These are pointing toward each other, so they can't cross, so they bend away from each other. Okay, think of this as leaf springs like you have on the trucks and things like that, right? And if they're bending this way away from each other, they're pushing each other away. So think of that as why these repel each other. Because these lines can't cross each other, They can't even touch each other because they're pointing in the same direction. So they bend and force each other apart, trying to get back to their original position. Okay? So that's what's happening with two like charges picked out. Of course, this is done on a plane. These would be in all directions. Yeah. Okay? This would be if they're different charges. This is a small positive charge. And that's exactly what the distribution of those would be like if there wasn't this charge here. This would be the distribution of this one if that charge wasn't there. See, it's almost uniformly surrounding that. But these are pointing away from the positive toward the negative. Well, these can connect because they're going in the same direction, not the opposite directions. So they do. And when they connect, they try to pull them into each other. So this is why you have attraction of unlike. Or this is how we visualize the field lines. Okay? And remember, the field lines always point away from positives and toward negatives. So just completes the picture here, pulling them toward each other. Okay. And I think the last topic we'll talk about today will be electric potential. Okay? This is a scalar field, not a vector field. Remember, force fields were vector fields. This is a scalar field. It has no direction associated. It's talking about potential energy, associated with potential energy. The unit for this is the volt. And I want to give you exactly what a volt is. They probably will give it to you later. Yeah, they will. So I may hold off on it. The unit for potential, scalar potential, electric potential, is a volt. It's not an energy unit. It's related to an energy unit, but it's not. We'll show that in a minute. Related to the work involved in positioning charges. Okay? So this charge up here, y'all still want it positive? Okay, if I were going to bring in a positive charge from infinity, out of infinity it doesn't even know this is here. But if I bring it in, I've got to do work to force it to come closer to this. Okay? So I do work on it. That's the potential. Okay? Has to do with energy. And that's a scalar quantity. It's not a vector quantity. Force is a vector, energy is a scalar. If I was bringing a negative charge in, this is still positive, right? Bringing a negative charge in, I'm having to hold it back because it's wanting to go right toward that. So therefore, it would be the opposite potential. It can have a plus or minus sign, but there's no direction associated. It's what potential energy I'm either exerting to force it in or holding back to keep it from flying in. Okay? The potential difference is important in producing forces and moving charges. It doesn't matter what the actual potential is, it's the difference in potential that matters. Okay? Remember when we talked about gravitationally? The gravity on this book is the same when I hold it down here as it is up here. But it's the difference in potential that makes the difference. Okay? That's probably a lousy example, but okay? But that's analogous to moving masses in a gravitational field. Where you put your zero reference level, everything depends on that. Okay? So, this is your fixed positive charge, the one I had hanging up here, remember? Let's call it 1 Coulomb positive charge. And then if I were to bring in 1 Coulomb from way at infinity up here and get it to bring it in, and I do 1 joule of work on that to force it in here, then this has a potential of 1 volt. Because what a volt is 1 joule per coulomb. Joule per coulomb, that's what a volt is. I was thinking they were going to show it here. Let's see if they do. Yeah, there it is. A volt is the work done divided by the charge moved. So a volt is a joule per coulomb. Now here's something bizarre about a volt. Okay, now notice work is capital W, that's the parameter for it, is measured in joules, right? Q is the parameter for charge. It's measured in coulombs. V is the parameter that represents voltage. And guess what we measure voltage in? Volts, which has the same unit. So this is one place where the parameter and the unit look identical to each other. The only way you can tell them apart if it's written as a literal equation with letters, this is the parameter, electric potential difference. If it had a number in front of it, that would mean 10 volts or 3.3 millivolts or whatever. So it's the same symbol. Everything else usually has a different symbol. Voltage, you use the same symbol for the unit as you do for the parameter, which is a little bizarre. Okay. I think that's probably a good place to stop. And I swear, I don't know what happened to my pencil. Did anyone borrow my pencil? It must be someone from the last class must have done it. Huh? Yeah, because I marked it on my last class, but I don't have it now. I've got another pencil. I can get one. It's just bizarre that it disappeared. Okay. It's kind of like that thermometer from the lab. What's happening here? We had a thermometer disappear last time. Huh?
Might have put some cameras up in here.
I'm not worried about pencils or but it's just strange that they disappear. Okay, so I will go on and end it today. Sorry about cheating you out of, what is it, 40 minutes out of your tuition dollar. But y'all hung in there really well.